Welcome to the CMU SEI Research Review 2020.
Well, good morning and welcome to the Software Engineering Institute's annual research review for 2020. I'm Paul Nielsen, the director and CEO of the Software Engineering Institute at Carnegie Mellon University. For 35 years now, we've been a DoD federally funded research and development center, FFRDC, managed by Carnegie Mellon. And just this summer, our contract was renewed through the year 2025. For all these years, we've been concentrating on software engineering and cyber engineering. And just about 2 years ago, DoD added the mission of doing engineering for AI systems to our list of things to do. So we're very excited about being in these really critical technologies for our time. Now we're coming to you in a little different format this year, just like everyone has had to convert to a virtual format since March timeframe because of COVID. And we hope it works well. We've worked hard to make it work well, but there's still some things that aren't the same. You know, we won't be able to do the networking that we always enjoy at events like this, and some of the other sharing that occurs. We hope we can get back to that next year. You'll find that our program today, tomorrow, Thursday, and Friday demonstrates ways our people at SEI and Carnegie Mellon University make a big difference for national defense and security. And you may note we took off Wednesday in the middle of this week because that's Veterans Day, and we want to celebrate veterans just like all of us should in our country. Now, the way we do this work is sort of through a multi-pronged approach. We do fundamental research in software development, cyber, and emerging technologies such as AI. We also collaborate closely with Carnegie Mellon University and other leading academic institutions around the country, around the world, really. And then we are very active in our participation in professional societies that are important to this business, like IEEE, ACM, INCOSE, AIAA, and even the National Academy of Engineering. Building what we learned, we produce results in the form of prototype tools, technologies, and practices. And then very importantly, we try to prove our practices by partnering and collaborating with the people that write these codes and build these systems to make sure that the work that we do works in practice. And sometimes, you know, we have to tune things a little bit when you see how they really work in practice. Now, we really look forward to working with you, conversing with you as best we can in this format over these next days. But we really hope that we establish a relationship that goes beyond these 4 days. And so we look forward to being with you in the future. Now, it's my honor to introduce the Vice President of Research at Carnegie Mellon University, Dr. Michael McQuaid. Dr. McQuaid is a 3-time graduate of Carnegie Mellon University. He then went off to a very distinguished career in industry before returning to Carnegie Mellon about 2 years ago now as the Vice President of Research. So Michael, over to you. Oh, you have to unmute, Michael.
There we go. Mistake
There you
number one. Thanks, Paul, and good morning, everybody. If I'm the last person who does that, it'll be a successful week. So let me welcome everybody both to SEI's Research Review and to Carnegie Mellon. This is the kind of welcome we do these days where we're all learning what it means to be both productive and virtual. And just as a bit of a side for those of you who are wondering, that's the story on campus right now too. Our students are 2.5 weeks away from the end of the live time on campus, up through Thanksgiving. Classes being offered live and remote, and the mission continues, educating the students who will help do the kind of work that you will see and hear this week, but also across the spectrum of what CMU does. So I'm very, very pleased with how well we've done. We have managed to bring our research back to campus and our students both virtually and in person. So happy for that. Looking on the good side, what's the impact of this kind of an event? So I remember speaking at last year's live event in the Simmons Auditorium. Excuse me one second, hold on. Sorry, thanks. Speaking at last year's event, we had about 150 people live and in person. We have over 700 people signed up for the event this week. So really a great chance to have people participate much more fully. Just a few comments on the agenda that you're going to see this week. Paul mentioned SEI's core mission around software engineering. How do we build software that delivers what we want it to deliver, and how do we do it efficiently and effectively? How do we protect ourselves and our critical systems, the cyber mission that SEI has conducted for more than 35 years? And now moving more and more into the question of what does AI engineering mean? How do I know what my AI systems do? And I think you'll hear 4 questions that get discussed, debated, and you'll hear about research over the course of this week. So first of all, what can I know about my AI system? How do I know it? What can I know in terms of what the system is either telling me it is doing or I am believing that it is doing? And just as important in combining 2 of the other missions of SEI, how do I attack an AI system and what do I do to protect an AI system from cyber attack? So you'll hear about all of those this week. And I think that kind of conversation will be most important for the research today, tomorrow, and into the future as we add that major important mission to the SEI. I also want to stress that part of the opportunity you'll hear today is about the coupling between what happens in the Software Engineering Institute and what happens on the main campus right next door at CMU. That strength of fundamental research and the SEI mission combined together is a reason that we can bring what we can to the national security infrastructure, national security mission here in the United States. So 2 things for me as requests for all of you. It is on one hand very easy to have this kind of conference and people can come and go and participate. It is harder to fully engage, and I would ask you to fully engage. It's harder to participate in dialogue, whether that's by chat or by raising your hand and participating, but I hope all of you do. There will be times when you listen passively, but the benefit of this week is by people really participating to the maximum extent they can. So hope you do that. And then my second request is just that everybody have fun. It's a big week full of a huge amount of content. I hope you enjoy it. I hope you take something away from it. And I hope you also give us feedback at the end as to how the week has gone. So with that, I'm going to turn it back to Paul and we'll get on with the program. Thanks everybody for joining us.
Thank you, Michael. Michael has added so much with his technical acumen and his industry experience to the Carnegie Mellon University team. So we're really happy to have him as one of our team members here. Now it's my pleasure to introduce Dr. Matt Gaston. And Matt has been with SEI about 10 years now. My, how the years fly, right, Matt? And but he came to us after being both a military person and a civilian at NSA and doing a little bit of a stint in industry as well. He leads what's called our Emerging Technology Center, which is the center that looks at a lot of things, but especially has been our lead for AI engineering. So Matt will be leading a session that talks a lot about AI engineering today. So Matt, over to you. Please lead us through this today.
Well, thank you, Paul, and thank you, Michael, and welcome to everyone out there. We're really excited to have all of you join us today at the Research Review and throughout the week. And we're excited to share our work, the work that we're doing at the Software Engineering Institute and at Carnegie Mellon University with all of you. So as Paul said, my name is Matt Gaston. I'm the director of the SEI's Emerging Technology Center and the head of AI at the Software Engineering Institute. The focus for today, the topic for today is one of the major objectives that we have at the SEI. We call it realizing algorithmic and computational advantage. There's a lot in there. I'm going to try to frame that for you to set up the day. It's really, so this idea of realizing computational and algorithmic advantage is really about leveraging emerging technologies, new technologies that are coming out of places like CMU, really across the nation and the startup community and industrial research, or even globally. There's amazing things happening in software technologies, computing technologies, and this idea of realizing algorithmic and computational advantage is about helping the Department of Defense, our sponsor organization, and related organizations to really tap into all of those amazing technologies. Our approach is really twofold. The first is we track, identify, and evaluate or experiment with all of these amazing new technologies. We do that by building prototypes, by building technology demonstrations, and by applying these new technologies in what I would call mission relevant domains or applications. So the first part is about knowing what technologies are out there and how they can have an impact on mission capabilities. The second big part of our approach is in solving engineering challenges associated with these new technologies and associated with integrating these new technologies into existing systems, workflows, patterns of organizational behavior. That second part is really, really important, right? Many of these technologies might exist in the lab or might exist in an isolated application space. And there can be major challenges to get them to scale or even just be usable in different domains. The size, speed, and complexity of mission applications can be vastly different than where these new technologies are being developed and experimented with at their sort of invention time. Our current portfolio of work in emerging technologies related to this idea of realizing algorithmic and computational advantage is really three parts: applied artificial intelligence, advanced computing, and human-machine interaction and teaming. In applied AI, we really talk about what I like to say is AI for mission. How can we take latest and greatest or even legacy AI technologies and apply them now in a meaningful way to mission capabilities? Missions like intelligence or command and control or logistics or even cybersecurity, which is also a special focus of the Software Engineering Institute. We also think about here at the Software Engineering Institute how to apply AI technologies to the process and practice of software engineering, which you'll get to hear about later in the week. So in AI, in applied AI, we're working in object detection, computer vision, remote sensing sorts of problems. We're also working in understanding patterns of sequential behavior, modeling patterns of sequential behavior, and even natural language processing. There's a lot to be done, and obviously a lot of applications of those types of technologies to DoD and related national security missions. Advanced computing is really the underpinning of realizing AI at mission scale, mission speed. We've been focused on advanced computing for many years now. And right as we speak, there's sort of a revolution going on, right? With the world, not just the DoD, but the world starting to focus on bringing AI to their businesses, to their operations, to their missions. People are realizing that there's an extreme computational cost for some of these AI technologies, like deep learning. Some of you may have heard about these new models. They call them transformer models. They're natural language generation models. The famous one now is GPT-3. It's estimated that it cost, $3, $4, $5 million to train this model, just to train this model once, in order for it to become a natural language generation model. So the computing platform that underlies all of these things is extremely important to the capability, the functionality that you can realize as part of it. And then the last one, human-machine interaction and teaming. Well, once you can, find and identify AI technologies that can augment or provide a leap ahead mission capability, and you can drive that with advanced computing, you then, not really after the fact, but you also have to worry about how these systems are going to interact with humans. some of the questions that Michael just posed. How do we understand that these systems are working? How do we know that they're doing what they're supposed to be doing? How do we know what's going to happen if they're attacked? This is all part of this sort of human-machine interaction and teaming work. That also goes to novel interfaces and other ideas like that. So I mentioned before, the second part of our approach is really about solving engineering challenges associated with these technologies. Sometimes we like to call this making the recently possible mission practical, which is exactly that. It's exactly solving these engineering challenges. And this has led us, as recently as about 2 years ago, has led us into the space that we now call AI engineering. And so AI engineering is really about the process, practice, and tools that are used to build, adapt, deploy, evolve, and operate reliable AI systems. And I think that word reliable, you could put other words in there, robust, other words like that, but the spirit of reliability, systems that we can count on, systems that we can know will work, have been built the way we need them to be built, and will work the way we want them to work, not just in the lab, not just at system integration time, but once they're deployed into the wild. And there's so much amazing work in AI, but not all that much focused on really making these systems reliable. And when I say AI system here, that's a system that has AI components as part of it, right? Many of the systems that you're going to deal with out there in the world don't just have AI components, they have traditional software components, they have data components, et cetera. They have hardware components, to say. I like to actually use a phrase that Michael used when we first started talking about AI engineering to drive it home, right? So let's think back to the history of the Software Engineering Institute. We were created in the mid 80s as the Department of Defense realized that this stuff called software was going to be really important, and they needed a place that worried about how to do software as well as software can be done. That's right where we are with AI today, right? The world is really paying attention to AI. There are many, many initiatives to develop, adopt, use AI technologies. And our focus on AI engineering is really about helping the Department of Defense, related organizations, and even industry organizations, where it makes sense, do AI as well as AI can be done. So to full credit, that's a quote from Dr. McQuaid, our Vice President of Research, but I think it really frames what we're focused on. So over the last 2 years, we have heard a strong demand from DoD leadership, places like DARPA and the JAIC, the services, the intelligence community, really sort of expressing their concern that it's amazing to see everyone surging towards the use of AI technologies, but not a whole lot of focus on, well, how do we do this right? What happens when we deploy them? How do we know if these systems stop working? What happens when they're attacked? So that's the focus of AI engineering. Now, you might be asking, why AI engineering? Why isn't it just software engineering, or why isn't it just system engineering? Well, I would say there's most certainly many aspects of software engineering and system engineering that apply to AI. But I think AI challenges those more traditional disciplines, or those disciplines as they are today, with a couple of key points. And you could select any number of different aspects of AI that might push on the boundaries of those engineering disciplines, but I like to think of three. The first is data. Modern machine learning technologies, modern AI techniques are really driven by data. And when I say driven by data, the functionality of the models that get produced from machine learning algorithms are actually dictated by the data that's used to train those systems. So data becomes this very, very important, if not critical, piece of the overall puzzle. And as you know, the data you use to train a system might be different than the data you see when you're operating a system out there in the world. So data as a core concept, as the driver of functionality of these systems, is a new emphasis when you start to build these AI capabilities. The second big difference, the second big sort of pushing the boundaries of traditional engineering disciplines is the prevalence of uncertainty in these models, in these systems that are built around AI capabilities. So most AI technologies are probabilistic in nature. They produce confidence intervals, and there's a natural uncertainty about what they're doing. They're only so confident in the decisions or recommendations that they make. And so you've got to build concepts of uncertainty into the overall system where you're going to deploy these, including the humans that have to understand how sure is the system about the predictions or inferences that it's making. And the last one, and I think maybe this is the most important one, AI technologies today are largely being used to automate and augment situations or tasks where humans do those tasks today. And that's not to say that AI will replace the humans. It's to say they're being put into place where we would normally expect a human to be making the decision. And I think that's really important, right? Especially when you think about defense and national security, applying AI in that way. We need to make sure that these systems are built to be reliable, to be robust, to be understandable and interpretable, and all of those things. Maybe most importantly, to know when they don't know what they're doing. So to sort of frame AI engineering just one level deeper, based on input we've received from the services, other components of DoD, the intelligence community, and some industry thought leaders across the academia and industry, we've identified sort of three core themes for AI engineering that we're focused on. The first is scalable AI. Scalable AI here doesn't just mean making AI go big, go fast, go up to the size and complexity of mission scale, but it also means how to get AI technology smartly adopted across an enterprise. So there's some thinking there on process and even acquisition and frameworks, et cetera. The second big piece, second theme of how we're thinking about AI engineering is robust and secure AI. Obviously, this one is very, very important in the defense and national security applications. Here, robust really means getting beyond just evaluating these systems on accuracy. Much of the work in modern machine learning is about eking out a little bit more precision or a little bit more accuracy in the task that's trying to be completed. We think you need to add metrics for robustness and other things to know that the system will actually operate the way it's expected as it sees different situations in the future. And secure there really means what do we do about the new attack surface that AI technologies present? They can be manipulated in interesting ways, and you're going to hear about that later today. The last theme of AI engineering is human-centered AI. And again, this one gets to that whole idea about these technologies are really going to be deployed in places where, or for tasks where humans were previously making these decisions or doing the analysis. And so it's really important that the AI technologies we build are human-centered from the start. Part of this is about understandability and interpretability. Some of this is about ethics. The DoD recently, within the last year or so, has adopted 5 ethical principles of AI. This is a really good thing, but there's also many questions around how do you actually implement those ethical principles into the systems that we're building. A major part of what we're thinking about with AI engineering, and a talk you'll hear later today. And then the last part of human-centered AI is really about culture and organizational readiness. We heard this most loudly from the Navy, and the importance of culture and how they will think about it as an organization adopting AI technologies across the enterprise. Okay, so that's how we're thinking about AI engineering. I thought I'd mention a larger initiative at CMU where AI engineering sort of fits and has some impact. And so our AI engineering work at the Software Engineering Institute is part of a 10-year research vision that's called AI Fusion at CMU. And I don't have much time to talk about AI Fusion, so I'll just briefly give you the teaser on it. AI Fusion is really, again, this 10-year research vision that looks at how to get AI scalable, very, very broadly, and usable in the world of all the complex data and distributed processing devices that exist out there. And so AI Fusion is looking at new algorithms that do distributed or federated or privacy-preserving capabilities. It's looking at new fabrics for moving data and models around a potentially globally distributed architecture of IoT devices and processors and data centers and everything else. And then it's looking at new computing paradigms that would allow AI capabilities to learn at the edge, but also then possibly merge and combine and different computing capabilities that might be needed at the data center. And so really stretching from the data center to the edge is a key focus of AI Fusion. So with that, my time for framing the day is about up. Next up is a panel that I'm really excited about on advancing AI engineering for defense and national security, where we'll hear from the director of the JAIC, a member of the Defense Innovation Board, a professor at Duke, and the director of science and technology at the Office of the Director of National Intelligence. And then this afternoon, we'll have several talks that are all along the themes that I've mentioned this morning. And I want to emphasize that at the end of the day, there's a poster session. And in that poster session, there's a real opportunity for all of you to engage, to go deeper with the researchers, that are doing this work. And so that engagement is really, really important, and I highly encourage it. So with that, I'll say thank you. Welcome to the SEI Research Review, and I look forward to the rest of the day. Welcome back, everyone. I'm Matt Gaston. I got to introduce myself in the last session, in the framing session, so I won't reintroduce myself. I did mention that I'm really excited about our first panel at the Research Review on advancing AI engineering for defense and national security. You'll see why I'm so excited about the panel as I briefly introduce our three panelists. So first, we have Dr. Missy Cummings. Missy is currently a professor at the Duke University Pratt School of Engineering and the Duke Institute of Brain Sciences. Missy is also the director of both the Humans and Autonomy Laboratory and Duke Robotics. And then notably, I think this is really, really interesting and important, Missy also served for 11 years as a naval officer, where she was one of the first female fighter pilots in the Navy. So welcome, Missy. Thank you so much for joining us. Next on our panel is Lieutenant General Michael Groen. General Groen is the new director. I think October 1st was the start date. The new director of the Joint Artificial Intelligence Center. Before his nomination to be the director of the JAIC, General Groen held many important command and leadership positions, obviously. Most recently, he served as the Deputy Chief of Computer Network Operations at the National Security Agency. My agency, as I like to say. I spent about 10 years there. And before that, General Groen was the Director of Intelligence on the Joint Staff, the so-called Joint Staff J2. So General, thank you so much for making the time to join us. We're really excited to have your perspective from the JAIC here today. And then last but not least, Dr. John Beeler. John is the Director of Science and Technology at the Office of the Director of National Intelligence, where he leads sort of all of science and technology for the intelligence community, is one way to say it. Before taking the position as Director of Science and Technology, John was a program manager at IARPA, where he led programs on secure AI and related topics. And before that, a practitioner in industry, a practicing data scientist in industry. So thank you, John. Really glad you could join us today. So the panel, the discussion is really focused on AI engineering and what it means to make these technologies, components, systems as reliable as possible as we think about adopting them and applying them and deploying them for mission capabilities across defense and national security. So with that, I'll invite our panelists to just provide some opening remarks, some perspective on their thoughts around AI engineering. And we'll start with Missy.
Thanks, Matt. Thanks for having me today. It's always great to work with Carnegie Mellon. And so I loved it when they called me to talk on this panel to talk about, AI engineering, what goes into the engineering of AI. This is an area I spend a lot of time in. So I often make the joke in public settings that I will never get into a driverless car that any of my students ever programmed. And that is absolutely the case. I don't trust them. So recently, as an example, we were doing a study for the Department of Transportation trying to correlate risk factors with crashes and pedestrian deaths. And the model came out in a particular way, and there was just something weird about the model. So I made my postdoc. Now remember, this is not even a student. Postdoc, asked about the cleaning of the data. Yeah, we got it all. And then something still wasn't working out right. And so I finally made them show me a histogram of age, how they were taking the age data. And then in the data set, we had a pretty normal distribution, except we had a huge spike of 90-year-olds. 90 to 100-year-olds, a huge number of drivers. And I told my postdoc, do you think that's right? Do you think we really have that many, aging drivers? And so what happened was, in the data set, the Department of Transportation, if they didn't know the age of the driver, they would just put in 99. So it was, the postdoc and the other student working with him, they just didn't even think that this was a deal. They just didn't realize that that was a possibility in a data set of millions and millions of data points. And so, that's a good example of, I'm sure everybody out in the audience is like, oh, I would never make that mistake. Yeah, trust me, when you're talking about huge data sets, it's easy to let one little outlier of a data go by and not realize what a major impact it can have on your model. But this problem of data cleaning is huge. I mean, if you know anything about machine learning, it's 95% of data cleaning, 5% of running a model, right? That's the time that you spend on the data set. The Navy recently gave us this beautiful data set of all the accidents that happen on aircraft carriers, and we're trying to develop a machine learning model to actually then figure out what the real relationships are. And I had a student quit the project because he had to do data cleaning. He's like, well, if I have to do data cleaning, I'm not doing it. And I have to tell you, he's not the only one. There are the students, just general, it's hard and it's boring and it's tedious, but that's actually what's so important about machine learning, is getting the data set right. And now you know why I will never ride in a car with any of my students have programmed. But this also goes to bigger issues. We've been doing a lot of testing with actual Teslas on a closed test track. And you can read these papers we just released on my website, so you can read them now. But the news is bad. The news, and it's different than probably what Tesla thinks. The systems are not performing consistently and reliability across Tesla Model 3s, or within even one Model 3 can perform wildly different under the exact same circumstances. So this tells us a lot, probably that the perception systems are really brittle. It's a black box. We're not sure how the autopilot technology, the logic that goes into that plays into the problems with the perception. But this is yet another example of it's critical to do testing in this way so that you can find out. These aren't really edge cases. When you go back and you look at the testing that we did, you're going to be like, wow, that's scary, because these are not edge cases. These are normal everyday cases. And so if we don't really appreciate that our technology can be so widely variable, and we have maybe some crazy data sets that you hired one of my people and they just didn't bother to check that outlier, then you're going to get these kinds of outcomes. And so I think it's really important for me to communicate to all of you that it's hard to get good quality data sets, and testing. I just can't emphasize that enough. All right, thanks, Matt.
Thanks, Missy. I thought you were going to tell us you solved the problem of always having pristine data, and I think we could all go further faster if we had that. But unfortunately, no, you haven't solved it yet. General Groen, any opening comments?
Yeah, sure. Thanks, Matt, and thanks CMU, and to everybody who's listening to us today. Really appreciate the opportunity to talk about how we're looking at AI engineering and sort of AI implementation across the department here. So the Joint Artificial Intelligence Center, the JAIC, our mission is to accelerate the integration of AI into the department, and then try to achieve mission impact at scale. And so, obviously, when you're talking about something as big as the Department of Defense, scale is everything. So we're trying to move, do niche, test cases to begin with, but then also think about how we're going to scale those across the department. And commercial industry gives us a lot of good examples there. Our vision is to transform the department through the integration of AI. And when you think about what the department does, I mean, there's the warfighting cases, which are really important, and I take Missy's comments really to heart. That we have to, just testing is so important that we get this right, and we can talk about that more later, I'm sure. But then there's also the business processes, right? So all of us are taxpayers, and we should all be interested in making sure that the department is making good decisions based on good data for everything the department does. And so efficiency, effectiveness, and then especially for the kind of a core ethic. all the young men and women that we put in uniform and send in harm's way today and in the future, it's really critical for us that we never put them in a position of disadvantage, right? We always want to make sure that they have the tools and the capability, the best on offer for them to be successful on any battlefield, wherever that occurs. One thing that's really that's really weighs on me very heavily is this idea of a transformation of warfare into the information environment. And why I'm so transfixed with that. If you look at the transformation of warfare in the industrial age or to the industrial age, it was horrific, right? Armies, people, nations were not prepared for the impact of the industrial age on warfare. And so, World War I, of course, was a horrific event. We have to think through carefully now, what are the implications of the information age on warfare? And so the effects will be different, but they may be just as lethal and just as dangerous to the young men and women that we have in uniform out there. We absolutely have to get this right. And we know those who would, be our opponents are taking artificial intelligence very seriously. They're exercising it at scale. They're building solutions at scale. And so we want to do that too. But while we're doing that, I mean, we want to be informed by the best ethical practice and best ethical grounding. We want to be informed by thought leadership, like the kind of thought leadership that we experience with CMU, MIT, Stanford, others. Like you guys are right on the cutting edge of understanding where the real problems of AI are. And so we want to learn from you, right? We want to engage you with in formats like this, where no kidding, we can talk about what's really important and what might we, what bushes might we want to look under to make sure that we're not missing something in the technology. So really appreciate the opportunity. I'm relatively new in the seat. I will. So Missy brought up data and data curation. I'll bring up another aspect that I think we could talk about, and that is, probably one of the most pressing aspects of AI engineering that we practice is the decision process itself, right? And so, and I'm thinking here less autonomy systems, but no, like decision support systems, and those are the kind of things that would influence a business practice or a warfighting process. Like getting consumers to be able to sit down and think through their decision process. How do you make that decision? What data do you depend on for that decision? What data is relevant? And getting some ownership of decision makers to their decision process is a necessary precondition for us to do effective AI engineering. And so it's not just the technology, it's the humans that are using this. And I'll just leave it there, and we can talk more about those things. Thank you.
Thank you, sir. I hear you talking there at the end about really human-centered design of AI capabilities, right? Exactly. The warfighter in the loop and the decision makers in the loop. Lots of questions come out of that, but let's go to John next, just for some opening remarks.
Yeah, awesome. Thank you. So thanks to Matt and CMU for putting this on. I think this is a hugely important topic, and look forward to seeing what falls out of this conversation and then the rest of the presentations kind of in this session. So before jumping into the AI engineering aspect, just kind of want to situate people on what the job of the intelligence community really is, right? And our purpose is to provide actionable insight to policymakers within a time frame that they can actually act upon it, right? So everything that we look at, similar to what the general was saying previously about warfighter support, right? Everything that we look at in terms of AI ML is to support that intelligence process. So none of this is AI for AI's sake. It's to speed up the rate at which we can produce such actionable intelligence. So to that, we have to consider, again, great points made previously, the whole system in which we're dropping these AI ML solutions. And because of that, we need robust, reliable, and repeatable processes so that we can quickly spin these things out, both at scale to the general's comments, but also in our applications in very niche use cases, right? Because we have some things in the intelligence community that we do that no one else does and even aren't scaled across the community, right? So we need to be able to serve a wide range of users and do that quickly in a repeatable process. And so that we can communicate to end users our confidence or even lack of confidence in some of these analytics, right? Because any piece of data that comes across as part of the intelligence cycle is only one piece, right? So we have all source analysts that look at a ton of information and roll out all that up to come to an analytic judgment. So what's incumbent on us as the developers of some of these technologies, and I really see it as fundamentals to some of this AI engineering conversation, is being able to communicate some of that uncertainty to the end users that aren't necessarily machine learning engineers and machine learning researchers, or to Missy's point, even if they are, right? Because there's lots of things that can go wrong that even if you're deeply steeped in some of these things, you can still have some misfires. So to the human-centered design points that were raised earlier, if we're deploying some AI ML system that has 95% accuracy, right, and not mathematical accuracy, but just generally, right, it's wrong 5% of the time. What's that mean when we're wrong 5% of our time in the intelligence cycle, right? How do we tell that to the analysts that are consuming some of this information that, hey, we either didn't pick something up or we're sending something your way that the algorithm says is X, but it's really not X, right? So again, the human-centered design and being able to communicate some of these processes for how we insert some of this tech into the intelligence cycle is hugely important. And to that, we need a lot of this engineering process from my viewpoint so that we can speed up the rate at which we can insert some of these things and transition. Because again, we have a lot of use cases that do parallel things that happen on the outside, right, and in the kind of common world, but we have a lot of use cases that just don't look like anything else that anyone else cares about. Because that's why we exist as the intelligence community, is to really focus on these low probability, long tail things that happen out in the world. So how do we take these solutions that are developed on the outside and transition them effectively into our own applications? Because of that, we need some empirical assurances, whether they're verifiable or not verifiable, mathematic proofs or not, on how robust these things are to a various set of changes. And, you know, Matt, I know you and I have talked almost to death about some of these things, so happy to dive more into kind of what I mean by some of these empirical assurances and the sorts of intentional misfires that we are concerned about in the kind of AI assurance, AI security realm, which for me falls under this broad umbrella of AI engineering. And then last but not least, from our viewpoint, I think you hear this every time a member of the community comes up and talks about AI, right? We released our AI ethics principles, and so that undergirds everything. And I think this engineering conversation is fundamental to that as well, right? Because that rolls in, how do we come to the decisions that we arrive at, both in terms of our own business processes, be that HR or counterintelligence or security, or on the kind of pointier end of the spear for the actual analytic judgments that we arrive at, and making sure that our ethics and morals suffuse that entire process from top to bottom, and how we do that in a way that doesn't require a bunch of people sitting around a table every time we want to deploy an algorithm, but instead put some process and some engineering around some of those ethical principles. So I'll leave it there. I know that's a lot, and I look forward to diving into any and or all of that over the next half hour or so.
Right there, I think there's a lot to unpack from all of those comments. So I'm a little bit worried that we only have a half hour left, but obviously there's ways to continue this conversation beyond this. I will just maybe make a mention. I am seeing some questions come in from the YouTube chat. So if people out there listening in do have questions, please post them and we'll try to get to them. I thought I'd stay with you, John, quickly, and maybe before we dive into empirical assurance measures. I really like this question in framing AI engineering. Not that I want to focus on failures, but are there specific scenarios that you've seen where systems didn't work the way we expected them? And really, I know some of them for you especially might be hard to talk about, but in the defense and national security space as much as possible.
Yeah, so, you know, like you say, Matt, for me, getting into some specifics on how things have gone sideways is a little bit touchy here. So, you know, you mentioned in the intro that I did have a previous life as a data scientist out in industry. So we'll maybe tap into one of those examples that is in defense and intelligence, but can talk about a little bit easier. And it's a little bit humorous. So was previously working on a defense project, and at a high level, the goal was to look through imagery, not overhead imagery, but just kind of pictures of things, and find pictures that had explosions in them, right? So this was kind of a counter propaganda program that we were working. So it's a DARPA thing. Lots of PhDs in computer science and statistics and electrical engineering working this, months and months ton of effort, and we go and we brief it out and we put it up on the big screens, right? And we have lots of people in uniform watching this. And so there's a lot of really good pictures of explosions and, terrorists and things like that. But a surprising number of when you zoomed in a little bit, turned out to be fried chicken. So imagine being in a room with, like the general here, lots of people with stars on their shoulders, and you have lots of nice explosions and terrorists, and then fried chicken. Because turns out when you kind of squint and look at it, fried chicken looks an awful lot like an orange fireball exploding in something. So that's kind of a more humorous example, and one that's kind of readily apparent when you look at the imagery. But kind of to Missy's point, this was a team of some pretty good, well-trained people working this problem. And, our big briefing had all this fried chicken up there. So figuring out how we automate some of these processes to check some of that, top to bottom, left to right is very difficult because, I think that database was terabytes of imagery, and it's just really hard to think, yes, fried chicken looks like fireballs. So that's something we need to account for in these algorithms. And especially under time crunches, right? If you're trying to pump something out, if there's some new analytic that you have to deliver, if there's some new use case that you have to address, and you're kind of on a 24 or 48 hour deadline, how do you account for all these things and do that in a repeatable process? That's kind of some of the failure modes that scare me, for lack of a better word, is how do we put the guardrails on this when people are doing their best, but there's just a ton of constraints that we have to operate under.
Thanks. General Groen, how about you? Is there a favorite war story bouncing around the Jake about a system that didn't operate the way we expected?
No compelling fried chicken stories I can tell you. But the back end of that I think is really important, and that is one of the things that we're struggling with in the department is the is adoption and ownership, right, on the part of users. And this is why we can talk about testing. Bench testing is great, it's useful, but you really need to do operational testing in the environment in which you expect that algorithm to perform. And so that's something that I think the services, across the department are doing a pretty good job of. Actually, they're really starting to get, they want to bring AI to the field, and no kidding, use it in representative architectures. But this whole issue of ownership is really critical, right? I think this is a concern of mine, is how do you, military judgment is something, especially for senior commanders. I mean, it's something that you incubate over decades. And so a concern of mine is that, those first early AI systems that are fielded or operationally tested, under their purview, if they don't match their intuition, not every military decision today, I would say most military decisions today are made based on your best assessment of what you know and extrapolating for kind of your expertise. When you shift to a data-driven decision environment, you're going to have the capability of producing much better decisions. But if for some reason that doesn't match perception, kind of like what military judgment would say to a commander, then we may lose time, right? Because I think the response might be, hey, take that black box away from here. It's giving me bad gouge. I can't trust it, so I don't want to be bothered with it. And all that does then is creates a window for, it sets us back and creates a window for our threats to continue to advance while we, kind of take a knee because of a bad interaction early. And so making sure that we help, destroy this perception of, a black box that some contractor puts on a decision maker desk, I think is critical. We have to communicate to users, and it gets to human centric. We have to communicate to users that what we're doing is modeling their decision processes. We're modeling their data. We're trying to build their use cases. And so they are central to successful design and implementation of any AI that we're gonna field out there, and that they need to be ruthless critics, but they need to be bought in to, hey, help us do this right, help us make it better. We believe foundationally that data-informed decisions about things that we guess about today is the recipe for tempo and the recipe for accuracy and better decision making.
So Missy, since you already shared sort of a failure mode story, I would welcome another favorite one of yours, or maybe some thoughts on the general's remarks here about mitigating barriers to adoption, right? The lack of trust that commanders or just warfighters in general might have when it comes to these technologies.
Yeah, I mean, I could lecture everybody all day long on these topics. I do want to revisit something that John said. I don't mean to start poking people in the eye so early in the day, but I do see that something that you said, and maybe you didn't intend to make this, fit everybody, but the idea that we're going to automate everything. The fried chicken story is a perfect example of like, we're just going to automate this. And the more we can automate, the better. And I appreciate why people want to do that. You want to reduce the workload of PED people processing, exploitation, and dissemination. The DoD is not looking at all the imagery that it's got. It can't analyze it all, but guess what? Neither can Tesla, right? So I think that's one of the things is, yes, there's so much data out there, but on the flip side, this is go back to the human machine teaming. And of course, I'm going to say this as the director of the Humans and Autonomy Laboratory, but I really believe that the growth of AI has highlighted, or should be highlighting to most of you, it is so brittle, right? AI in the fried chicken story. And John, I'm going to use your story. I hope you don't mind. I'm just going to gratuitously throw it in and talks to the future, because I think it's a classic example of, look, these technologies are great when they work, but they can be so narrowly focused and good in just one small area. And if you deviate from that very focused beam, then you're going to start having a lot of problems and a lot of mistakes. And for the DoD, as a former warfighter, I'm very sensitive to a concept we know, of decision bias, where people it's automation bias, where people just believe what the automation tells them because the time frame is so short. I myself have done it in training where I have shot down blue on blue. I've shot down my own guy because there was too much information coming at me, and I pressed the button thinking it was the enemy, not realizing it was my own person. That is exponentially the problem that we've got in today's warfighting. And so I think I am both from an academic perspective, but also from I've been there, done that perspective. We really need to appreciate that human judgment, especially anything requiring visual discrimination and potentially the loss of life, even blue on blue life. We need to be really careful about making sure that humans are in a supervisory loop, and at least for now, until we can actually improve the technology. But I do want the Department of Defense should pay very, very close attention to what is happening in the driverless car world. Look, I got bad news for everybody, and a lot of CMU people are going to disagree with this. You're not going to get your driverless car. It's not happening, not in my professional lifetime, because the perception problem, the brittleness problem is, we can't do it for driving, which is a much more predictable world than warfare, right? So we need to just go ahead and accept we can't get there from here, at least in terms of where you think you were going. But that doesn't mean that we can't have even better systems if we can figure out the human machine teaming correctly.
John, I feel like you should have a moment to respond to Missy's comments.
Yeah, got thoughts. No, so the first, totally agree, right? And I completely agree that some of the thought on, AI is the magic dust that you sprinkle on any problem and you can automate it away. It is misinformed at best, right? So very much agree that there's a lot of hard problems and how brittle the things are, as the fried chicken story highlights. Feel free to use that. Instead, I think kind of to the point of this panel, this AI engineering concept is really how and where do we best insert AI and machine learning into the TC-PED process, right? Because right now it has been a human-driven process, and largely it's the same process that we've had since the Cold War. And instead, we're focused on pinpointing individual aspects of that TC-PED process of tasking, collection, processing, exploitation, dissemination, and automating individual snippets of that process that a human would do. rather than looking at the totality of that system and saying, how do we best pair AI machine learning with human analysts, both in the individual kind of collection and analytic stages, as well as the all source analytic phase of that. So I think there's a lot that we just don't know about how to best insert things. So we're, someone once called it the cat spotting problem, right? So we're kind of in the cat spotting problem. Like, look, we're able to pick out this thing from overhead imagery and say that it was there, right? And instead of really considering how do we best roll this whole system up and free up analysts' time to do some of the more high-level strategic intelligence analysis that we really want them doing, rather than hand jamming Excel spreadsheets together or something like that.
So there is a question that came in from Robin via YouTube, and I'm gonna modify the question slightly because it's right at what we've been talking about. As we think about these systems, right? AI components, AI technologies, integrated into larger systems, and those systems are integrated with warfighters and people. There are weaknesses in all parts of that system, to include the humans. I'm wondering if anyone has any thoughts about balancing the weakness, the brittleness of the AI technologies with, you know, the bias and shortcomings of even the humans that are in the systems. I'm guessing Missy has.
Well, I'd like to just jump in. And of course, I'm going to tell you, I have many papers on my website that will put this out in detail. But I have actually developed a framework that talks about, you know, autonomy works best in environments of low uncertainty that require high and fast computation. So, for example, autonomy does a great job. It flies planes way better than humans can. When I was operating around aircraft carriers, it just blew me away. And in fact, that was the motivation for why I left the Navy and went into academia, because I saw that planes could land themselves so much better than humans ever could on an aircraft carrier. And what was worse, actually, at least you got to sort of be in the loop when you were landing. When you took off in the F-18, you actually had to show everyone you weren't touching anything, because if you touched anything, you would only screw it up, because the automation had this wired and you should not be involved. And so that really opened my eyes to this idea. Look, there are some arenas where humans really, you know, the autonomy can do so much better. Taking off, landing around a carrier. Look, fighter pilots are over. I mean, we really don't need them except for maybe some very limited applications. And I know people, you know, they think I'm some kind of traitor, but the reality is most of those jobs can be automated. Forget autonomy, it's just basic automation. Where we still really need people are making those decisions about when to fire, making the decisions about what happens when something goes wrong. No mission I ever flew actually came out the right way, right? So how would we balance autonomy with humans in this case? The automation can help with that mass crunching of data, sorting through images, maybe triaging images and getting to the person at the right time, at the right place, and letting the human bring judgment and expertise to bear.
General Groen, thoughts on this? And I also want to bring back your comments about adoption, and maybe hear some things that the Jake is doing, getting people more comfortable using these technologies.
Yeah, I mean, the first thing I would say, I mean, we shouldn't throw the baby out with the bathwater here, right? So you know, autonomy is a really hard problem, and it's probably the hardest problem in the stack. But there are, you know, a host of AI applications short of autonomy that can have a tremendous impact on you know, on human decision making on the battlefield. And that's you know, for airplanes, that's interesting. For I think about, you know, a squad leader or a platoon leader who, you know, who's leading a section or a platoon, you know, into into a hostile village or into a hostile area, and you know, it comes under fire. Okay, having you know, not only the intuition that comes from your training and experience, but no kid, now have data that you can help make good decision making is critical, right? So you know, if that squad leader was informed by a virtual reality or an augmented reality headset that included, you know, objects that were detected, you know, maybe based on muzzle flashes or something like that, if that platoon leader had access to what fire support was available to him or her, so that, no kidding, you can make good decisions about what to ask for and how quickly to get that fire support. So like these things, I mean, just to, riff off Kahneman, so we have thinking fast and slow. We have the intuition that our military members will bring to a fight. So that, that intuition, the intuitive part is fast. Then if you can augment that with data, right, that, no kidding, what's available to you right now? Where is that threat actually coming from? Which buildings are most suspect around you? Where did you detect weapons, in this crowd? That kind of stuff allows you to do thinking fast and fast, right? Because now you're not only operating off your intuition, but you're also operating on the things that you've observed in the battle space. And that, that kind of links all of these things, right? So what John was talking about, now if you can get your intelligence feeds, in a predictable architecture that flows that data into a, as a service, and you create the platforms in the environment where, no kidding, now you can provide data as a service, whether that's weather, whether that's, detections from intelligence, whether that's, whatever you need. That's how you scale, right? So now every squad leader can enjoy that, every platoon leader, and then you just kind of go up the chain, right? Every battalion commander, every brigade commander understands not only the specific aspects of what they're facing today, but they know the logistic status of their units. They know which unit, might have some casualties and isn't a full up round, that he can use effectively in the next, in the next day's fight. That's the kind of decision making that I think intuition combined with data will be an immense service. And we'll get to autonomy. It's, autonomy is exciting. It's the shiny object. There's so much more, though, that we can do in addition to just autonomy.
Yeah, the thinking fast and fast line would be a fantastic conversation to have with Kahneman himself, because there might be, you might lose some of the human power of thinking slow in that case, right? The system two thinking. Yeah. So I want to transition. I want to sort of hard pivot. It's always one thing that's hard to do on these panels. And really give you a magic wand, right? If you could have some problem solve, some AI engineering problem, some piece of it, where you could, wiggle your nose and solve the problem today, or have it in the Jake as a tool today, what would it be? And maybe we'll go back to John, just because I think he's maybe not talked the most recently.
Yeah, so the list is long, so I think the hard part is picking one. But I think the one that I lean on most is something akin to a continuous integration, continuous delivery pipeline, but for AI and machine learning, right? And we haven't dove into it on this panel, but there's all sorts of ways that an adversary can intentionally break your machine learning model, right? So adversarial examples being the most common that people know about, right? So how do we test against some of that stuff automatically, right? How, if you're a developer, can you automatically run your model against some known vulnerabilities and have it shake out whether your model might break against something certain? To Missy's point, if people are coding, NAs as 99, right, it's doing some detection of that. Basically just ability to automatically, whenever you run some new code and push it to GitHub, it pulls it, and it's like a, test run or something like that against all the things that we have concerns about. And if it's truly a magic wand, including some of the ethical things that we've been talking about, right? So, hey, the example of, I forget which company it was, but the HR bot that ended up only hiring a certain type of person because that's all that they had hired before, right? So being able to account for some of those things automatically, because I see that as kind of one of the fundamental hurdles to really being able to deploy these things at speed and scale, and having some confidence. And since it's magic, having it be perfect, because as soon as we start running tests, right, then you say, look, I passed all the tests, so of course my thing's perfect, so I'm going to push it out in production now, and never worry about it being wrong. So a perfect CI/CD system for AI and machine learning would be my magic wand.
So to summarize, lots of problems, hard to pick one, so I'm not going to pick one, right?
Look, Matt, if you want to give me another half hour to talk about all this, I'll be happy to.
I would love to have another half hour, but we are rapidly approaching the end of our time. So, Missy, let me put that question to you. If you could wave a magic wand and solve some aspect of AI engineering, what would it be?
If I could wave the magic wand, I would have a massive infusion of dollars to educate people about AI. Specifically, I would grow a workforce inside the DoD that understands not only the fundamental underpinnings of AI, but then how to orchestrate the requirements, development, design, testing, program management. I think the thing that I'm concerned the most about is a profound lack of understanding all of the elements that you need to understand so that the DoD can build AI in, as the general said, these are not just platforms that we're talking about. We're talking about capabilities, processes, data management. I mean, it's a huge problem. And General, I'm appreciative that you just stepped into the Jake's job, but we're looking at a transition of power in the administration. And the thing that I'm worried about is that I thought we had, a head of steam, going for building AI, but if we do not get serious in this country, and by the way, this isn't just the DoD problem. I think it's a problem for the DOT, the DOE, most of the, and for medicine, and oh my God, it's a lost cause in medicine. But we have got to do something serious about growing a workforce that is competent at all levels so that people can build the right programs, insert the right technology in the right places, and test the technology in the right places.
Thank you, Missy. General Groen, magic wand, or even responding to Missy's comments about workforce.
Yeah, Missy, I am with you 100%. So we have got to build the environment, kind of the ecosystem of understanding AI, and that includes, like education is one of our primary lines of effort. I think you also, Missy, mentioned the level of investment, right? And so we are at risk of missing this transformation if we don't get after all of these aspects. I would say especially test and evaluation. I mean, if I had a magic wand, it would be in the area of explainability and test and evaluation, right? So validation, verification. How can we ensure that we are getting good answers? How can we ensure that our data isn't optimized against the wrong problem? The kind of the classic, the cure for cancer that actually that cures cancer but kills the patient, right? Like we can't. We have to be able to understand these things. And so a test and evaluation paradigm that based on ethical principles is where we have to be. And I don't think anybody disagrees with that per se. I mean, I've never met anybody who said, no, we don't need that ethics stuff. But no kidding, it recognizing its foundational role as a basis for our test and evaluation, explainability, and most important, trust. If senior leaders in the department don't trust the AI, then we will have missed it. We'll miss the transformation. And so that to me is key. We just have to make sure, this is a continued education program. The workforce, yes, but also decision makers and then policy makers, especially in the new administration, that no kidding, we make sure that we don't lose continuity and progress on where we are with artificial intelligence integration.
So I have so many questions, a few of them, my own thoughts related to all of this, but we are running preciously low on time. So I want to give each of you a chance to final thoughts, at least for this panel. I don't think there'll be final thoughts for AI engineering. There's much work to be done. The order, well, I was thinking we would go Missy, John, General Groen, if that's okay. So please, any final thoughts? We have about 3 minutes remaining.
Yeah, I think we need to do more about this AI, the engineering of AI. So I really think that what you've done here is great. I don't see enough of this talking. NSF is missing this. So definitely whatever I can do to help you grow this is because this is a fundamental foundational issue.
Wow. John?
Awesome. Yeah, so I like to leave these things with a little note of hope because I tend to see that a lot of these kind of panels on what's wrong with AI, leave me feeling a little bit down. So I think the promising aspect of this is conversations like this, right? And the increasing recognition that we need, that there's a lot of work to be done to make this stuff real, but there's very smart people talking about it and getting after it. And so just to quickly call out, there was a new framework released. I think, Matt, some people from Carnegie Mellon worked on it, as 12 institutions, including companies like Microsoft and FFRDCs and things like that, looking at the various failure modes of artificial intelligence and machine learning. I think it's in MITRE's GitHub right now. But again, just the increasing recognition of the fundamental nature of this, not just in kind of our nerd wonky national security arena, but, at Microsoft and at big companies like that. So that's what gives me kind of hope that we can tackle some of these really hard problems for national security, is the big brains that are working on this problem already.
And thank you, John. General Groen, final thoughts.
Yeah, first of all, thanks to CMU, the SEI, and the Emerging Technologies Center. I mean, we're the JAIC is an implementation organization, and so we feel a kindred spirit here, and we really treasure our academic relationships because we learn so much, and we want to stay where the thoughts are. I think everything that John and Missy said there is right on the mark. There is some good news, right? I mean, we have had some real victories, in things like, helping firefighters fight wildfires in California, right? In distributing humanitarian assistance and being prepared for disasters, anticipating failures or shortfalls in supply chains, against COVID, against hurricanes, so like there's actually lots of really good stuff that's coming through the pipe. It's simple right now, and it's kind of maybe the easier cases, but that's where we're going to cut our teeth. And that's where we're going to, if we do that right, and we keep approaching it from we need to test, we need to evaluate, we need to be ethically grounded. If we keep pushing that, that thought process in our own minds, we will gradually move up the value chain in AI instantiation in places where it does start to get harder. And so, this is a transformation that's coming. We're either going to get on it or we're not going to get on it. And the consequences of not getting on it are pretty severe. And we've got the great academic base, the great industrial base for creative thinking and data engineering and AI application. So, I mean, this is our superpower as a nation. Let's leverage it and get out in front of the wave. Thank you very much for the opportunity.
Fantastic. Thank you, sir. Great comments from everyone. I would love to spend, 4 more hours with this group and probably a handful of others that we can think of immediately to dive deeper. But that's all the time we have. I did want to mention we have launched a national AI engineering initiative. I really think of it as a movement. Dr. John Beeler happens to be one of our first sponsors of that initiative. We're already connected with the JAIC, sir, so that's the good news there. And Missy, you just volunteered to be a part of it, so that's really fantastic. Thank you to the panelists. This is a great set of exchanges. As far as I know, next is a break, and we come back at 12:35 to kick off some of the research talks from the SEI and our CMU collaborators. So thanks again to the panelists. This was fantastic. I think that's a wrap.
Welcome to the CMU SEI Research Review 2020.
So human machine teaming, right? It seems like this really complicated world, because not only are we dealing with human problems, but also this world of machine problems, and all the kind of uncertain, really soft and sometimes really technical world in the middle. And so what does it even mean when we say the words human machine teaming?
Yeah, so I think about it as not just a machine, not just software, but rather some type of complex system, an artificially intelligent system that has the ability to do some things and to support a human in the work that they're doing. So they're actually working together and sharing knowledge, sharing information, and determining how they're going to use that to work to each other's strengths and support each other in solving some bigger problem.
the goal was like I want to build a body of work that lets me do that, lets me do more of how do we take ANML and impact human lives. So while I've been at the SEI, I've led a small research effort focused on robotics and specifically how robots understand anomalous behavior, not only in their environments, but also as they interact with different humans in their surroundings. And so that's been a lot of fun. So we've done a lot of work with inverse reinforcement learning to understand anomalous robotic behavior. Separately, we've done a lot of work with remote sensing, EO, or sort of like electro-optical imagery or synthetic aperture radar imagery, and understanding like what are different parts of the world which are damaged or which are, about to be flooded or whatever. And then some like auxiliary work in just like adversarial machine learning or some other cool stuff. So really merging all of those gives me, I think, a broad platform to talk about how we can take ANML and directly use it to help human lives directly, whether that be directly through their health, like it's actually impacting the way they spread diseases or the way they understand neuronal sheet damage, for example, or more abstract, like how do we assist first responders and disaster people to better understand what parts of the world are damaged after disaster so that they can better plan logistics and resources, which then goes on and impacts human lives.
So we talked before about some other projects you've worked on, like the Defense Innovation Unit's XView, that kind of led up to this. Can you talk about that a little bit?
Yeah, so there's this team of people in the DoD, and they're called the Defense Innovation Unit. They're based out of SF, and there's a small team in the Pentagon, I believe, SF. In Boston, San Francisco, and Mountain View. And what their goal is to basically take some really, really cool commercial technologies that are available from startups or wherever in the world right now and translate them over to the DoD space to be highly applicable and impactful. So one thing that DIU focused on last year, back when they were so-called DIU experimental, because they weren't sure if that unit was going to do a great job, and they are, was they said that this whole world of operationalizing computer vision stuff that we do with satellites is really important. Like, it's not sufficient to just create prototypes and say, yeah, we can detect buildings or something. Let's get that in the hand of someone, who can actually do something about it, like who needs that information. So last year, DIU launched this thing called the XV1 competition. They created one of the largest overhead satellite imagery data sets where they had millions of buildings and just millions of objects overall that were very fine-grained. So they had everything from like a pickup truck to a pickup truck with a trailer, except like these objects could be really small in the image. So like it could be like identify this as a pickup truck versus pickup truck with a trailer, and the thing is like 5 pixels wide, and it could be really dense. Like there could be over 1,000 objects in one small image, and so it could be really, really dense detection. The issue with XV1 was that like they weren't able to do the whole operational part of it. Like it's a really cool research data set. It's really hard. Like we competed in that and we got 5th place in the world. And in my opinion, our metrics weren't anything great. Like it was okay. Like we got like a mean average precision of like 0.28 or whatever. Which again, on comparable data sets that aren't this difficult, the same model that we use could get a mean average precision of like 0.8. So like just for a comparison of the gap, like there's a lot of work to be done in this area. So it's a really good academic research data set, but it wasn't clear how to like make that useful for anyone doing operational work at the moment. So the goal was, DIU then reached out to us and said, hey, you guys did really well on this challenge. Would you want to help us figure out what we want to do for the next one? That's a little bit more operational. That's a little bit more impactful, but still involves computer vision in some way.
Right.
So we went through a whole bunch of ideas. We talked with USGS. We talked with FEMA, NASA. We talked with all these people who have all this data and all these amazing problems that I got to realize for the first time that like these are problems real people have to solve every day so that we don't get completely screwed when the next hurricane hits or whatever.
Right.
And so we ended up deciding on creating a challenge that lets people understand or lets models detect how damaged a building is after a disaster. So what happens is, I use California example because they do a pretty good job of it. After, let's say, a wildfire in California, they have about 24 to 48 hours to make a presidential declaration of emergency. And that lets them National Guard be militarized, it lets them do all these things that like enhance their response to these fires. And so what they have to do is they have to go in and give the give the declaration like we have 17,351 damaged buildings or whatever, and so we need help. That's a really exact count, and the way to do that is they literally send people in after disaster within 24 to 48 hours, and someone has to sit there and like count buildings.
So this is manual.
It's manual, and you can imagine how dangerous. Like if let's say it was a flood and there's down power lines in the water, and there's I don't know, alligators roaming the streets, or like looters, I don't know, shooting places up. Like you don't know, right? And so it's really dangerous to send people in after disaster to go and do this task just to declare emergency so you can get more help.
Right.
So the idea was like this happens everywhere. This happens in California, North Dakota. It happens around the world, in Nepal, everywhere. Like you need to be able to figure out what's damaged, how damaged is it, so we can not only do declaration of emergency, but we can also then respond accordingly, right? Like if I don't know this village is damaged in this remote part of Nepal, how am I going to get help or logistics or resources there? I'm not.
Right.
So what we've gone about and done is we've collected now this via our partners at Digital Globe, which is now Maxar. They have this amazing repository of satellite imagery from before and after disasters. We've gone in, we've collected that data, we've annotated it with not only where those buildings are, so polygons over buildings, but also we worked with partners at CAL FIRE, the California Air National Guard, FEMA, NASA to create this scale that lets people assess on a scale of 0 to 3 how damaged a building is. Is it not destroyed, minor damage, major damage, or destroyed?
First, give our listeners sort of a what is it? What is the foundational kind of concept of quantum computing, and why is it difficult?
Oh yeah, so fundamentally, it's about using new devices as the fundamental unit of computation, and these things are called qubits instead of classical bits or C bits, as they're sometimes called. And there are operations and behaviors of these qubits which are clearly different than classical bits. And these different behaviors potentially allow you to do things that are not able to be done on classical computers, or sometimes called classically intractable. And that just basically means that some computational task that you'd like to accomplish that has some use, we would like to do them on quantum computers, and we'd like to do them a lot faster than on classical. And so I think there's a duality. Like it's difficult for a few reasons. One is because it's still quite new as compared to classical computing and classical algorithms. And it's been like the better part of a century we've been working on that problem. Whereas for quantum computing, the idea for it was really sort of solidified in the late 70s, early 80s. And then algorithm development has only taken place over a few decades time frame. So I think there's great potential for the technology, and I think that's also what makes it hard. In some sense, it's two things. It's hard because it's new, and it's by and large unfamiliar to computer scientists and people like that. And then second, I think it's hard because the potential power that's there is tremendous.
The SEI doing? We have an initiative called Quantum Advantage. So would you explain that to our viewers and tell us why is that important that we have this initiative, and what is it's important to us as well as to the federal government?
Yeah, so I would say that I think the way that we pitch our initiative in totality is like the search for quantum advantage, which I would say is also the what's driving most companies and researchers in general. And what people think is an example of quantum advantage was the Google quantum supremacy demonstration that happened last fall. And the definition is there's some well-defined computational task that we can execute on a quantum computer and a classical computer. And the question is, for that computational task, does the quantum computer outperform the classical computer? And there's a few different ways you can measure outperform or performance, but this is really the bottom line. So like we're spending all this money on quantum computing and spending all this time researching and developing them. What are they really good for? And maybe one step further, what are they game changing for?
Right.
So that's definitely like our initiative, and our goal is to try and find to find this quantum advantage the soonest. So there are a lot of things that we can look out on a 10 to 20 year time frame and say, if we have a big enough quantum computer with high enough fidelity qubits and operations, then we know we can do these classically intractable problems. But the harder problem is in the next 5 years or less, what is the answer to that question? So what applications will we find quantum advantage for?
The SEI is leading a national initiative to ensure that our nation's AI capabilities are built, operated, and evolved well. AI is already transforming DoD missions by helping human users go further than ever before. As we develop new AI capabilities, AI engineering can provide the roadmap to repeat our successes in designing models and algorithms, to integrate AI components into systems where they need to work with traditional software, to manage data and our computational resources, and to define the processes and policies that center ethics, mitigate bias, and uphold the trust of human users. Join the movement towards scalable, robust and secure, and human-centered AI.
Welcome back, everyone. It's Matt Gaston again. This is actually the last time you'll hear from me for the research review, at least as part of the main stage. Thank you again for joining us. I'm excited to kick off really the afternoon session of technical presentations, discussions, and into the poster session. This morning we heard about sort of the need for AI engineering, not just me and SEI and CMU saying we need to do it, but the Jake and professors from other universities that are part of the Defense Innovation Board and the intelligence community. We're obviously very excited about this, and we really recognize the importance of both applying AI to mission capabilities, but also engineering these systems as well as they can be engineered. When I asked a question of the panelists earlier, what problem would you solve if you could wave a magic wand? There were really three answers, sort of boiling it down. One was continuous integration, continuous deployment environment where it's tailored to the special needs of AI and machine learning. Another answer was test, evaluation, verification, and validation systems for AI technologies that were informed by the ethical principles that we want to be a part of these systems, or need these systems to abide by. And then the last was really workforce development, right? Creating not just in the DoD, but in all organizations that are looking to adopt AI technologies, an organizational readiness, a workforce readiness, so that they're prepared to ask the right questions, to know how to acquire and deploy these systems. The good news is those three magic wands really do frame magic wand answers. They really do frame the rest of the day for us. So for the rest of the day, we're going to kick things off where, Dr. John Beeler had mentioned adversarial machine learning and the new attack surfaces that machine learning can afford in these systems. We're going to hear a lot about that in a project called Train But Verify. Then we're going to go dive deep into mission capabilities, where we look at advanced technologies for summarizing and searching video. And you can imagine all of the numerous applications of that type of technology. And then after a short break, we'll have a talk on ethics, specifically ethics as it relates to AI engineering. Not so much about just ethics in general when it comes to AI, but what do we do about these ethical principles? And how do we move towards the ability to know that the systems that we're building are part of that? And then we'll switch and look to the future. We're really focused on ideas around robust AI. How do AI systems, modern machine learning systems, know when they don't know, right? So how are they appropriately calibrated? How do we effectively model uncertainty in these systems so that as they're faced with new situations, these systems themselves can say, hey, I don't know what to do in this situation. Maybe I need some retraining. Maybe I need a human to come help me, those sorts of things. And also that leads to problems in what might be called open world reasoning, right? How do I deal with new situations? And then changing gears again, we'll go into a talk on advanced computing from Dr. John Wolbier. That's going to be motivated by a particular class of problem that I think has broad relevance, but it's really also going to get at sort of the shift that we're seeing in the computing hardware industry, and lots of different companies now building custom hardware for AI that's going to allow it to operate at the size and scale that we need it to. Then we'll hear from our CTO, Tom Longstaff, to put it all together. and then we'll conclude the day with the poster session. And I can't emphasize enough that please do join for the poster session. That's a great chance to interact in a deep way with the researchers that are doing so much great work at the SEI. So with that, thank you very much. It's been a fun morning. I'm going to turn it back to the team.
Hello, my name is Nathan Benthodness, and I'm here to talk to you about Train but Verify, which is about getting towards practical AI robustness. First, a word from our lawyers. And now that we've put that up on there for a second, what do I mean about AI robustness? AI robustness, in my case, the way that I like to explain it to people, is actually from the side of an attack. A popular taxonomy is the Beeler taxonomy, which states that a attacker can make an ML system learn the wrong thing, do the wrong thing, or reveal the wrong thing. Those are obviously the wrong things to do. When we talk about learning the wrong thing, we're usually talking about data poisoning or Trojan attacks, such as the original BadNets paper by Gu et al., where what they did is they poisoned the data to make a neural network believe that a stop sign with a sticky note on it was in fact a speed limit sign. We can also think about doing the wrong thing as the adversarial glasses, which was a classic paper, one of the first physically realizable adversarial attacks where someone could actually put on these glasses and fool the facial recognition system, or revealing the wrong thing, where what I give here is Fredrickson's model inversion paper, classic example of starting with noise and a trained model and then using an iterative procedure to recover the training data. You can see, for example, that the recovered image looks a lot like the person on the far right. So these are the things that an attacker can do. Well, what can a defender do? So this is what I like to think of as the train but verify grid. On the rows, what we have is we have training an ML system to not learn the wrong thing, right? To enforce a learn policy. Training a system to enforce a do policy so it doesn't do the wrong thing, and similarly for reveal, so it doesn't reveal the wrong thing, right? And if you put all of this effort into training your ML system to not learn the wrong thing, one of the things you're definitely going to want to do is you're going to want to verify that it didn't learn the wrong thing. And when you have that kind of matching training and then verifying posture, that's where you get a lot of the current work on that diagonal. So for example, IARPA's TrojAI program, DARPA's GUARD program, and a variety of other programs led by particular agencies. However, although there's a lot of work that needs to be done on the diagonal, for the DoD to get practical use out of this research, we have to consider more than just the diagonal, right? The DoD often does high stakes actions. And so they're going to definitely make sure that their systems are trained to not do the wrong thing, but they also often train on sensitive information. So they also need to make sure that they don't reveal the wrong thing. So what happens here when you in fact train a system to not do the wrong thing? Does it reveal too much? Well, it's been known for a long time that when you defend against do policies, your adversarial examples that you generate against those models do in fact reveal some information about the training data. This is a chart that we used to motivate one of our recent papers. In the chart, you can see on the y-axis we have the accuracy of the model, and on the x-axis we have the amount of changes that an adversary can make to a given image in order to fool the model. We have two different models compared. We have a model that is in blue, the standard model, that is not trained in any particularly robust way. And then we have a defended model, which in this case is actually trained with Madry PGD. And so what do we see here? We see that the model that is standardly trained, or is trained in the standard fashion, it starts off with a picture of a bird, and then the adversary adds an imperceptible amount of noise, and now the accuracy completely tanks. And the standard model is not robust to adversarial manipulation. And if we go all the way to the full strength adversary where they can change a whole lot of the image, it just looks like a noisy image of the bird. We didn't learn anything about the training data, but we also didn't have any robustness to this kind of attack. For the orange curve, we see different behavior, where over time, as the strength of the adversary increases, two things happen. One, the accuracy goes down slowly, but also the image itself begins to resemble something that you would expect from the target class. So for example, as we move from bird to ship, it begins to look like a ship. So there's not really a surprise that when the adversary can make your image look like a ship, that your classifier thinks that it's a ship, right? And that's one of the things that happens with these do policies, in some sense that they work, and so they end up revealing information about the training data. So that's a nice academic example that shows how you can do it. What about a more practical example about the kinds of information that you can learn? So here, what we go over is, again, we go over a model that is making high stakes decisions. So it has a do policy that it's enforcing, and it also has a reveal policy that it needs to enforce because it's trained on sensitive data. The attacker's goal in this case is to understand how a particular class, in this case the horse class from the CFAR10 dataset, was collected. And what the attacker is going to do is they're going to generate a series of adversarial examples. So if we start, for example, if the attacker starts at that seed column where they start with the white horse, the brown horse, and the other two horses, then what they do is they generate, starting with that seed, an adversarial example for the deer class. What we can see is that now the model shows that these images look, in fact, like deer, where they have antler-like structures, right? And then if they go back to the horse class, what's the horse image that looks the least like a deer? It's a deer, it's a horse that has a rider on it. And at least to my eye, these look like they have riders on them. And if you then go ahead and dig through CFAR10, you'll find that about 20% of the time, the images of the horses do in fact have riders on them, which shows the manner that they were collected. They were collected by people taking pictures of each other riding horses, not necessarily the kinds of images that you would see if you were just buying horses or selling horses, where there'd be pictures of the animals themselves. Right? So we've revealed, in some sense, a toy example of the kinds of information that you can learn about the training data. Okay? And so the objectives of what we're going to go through in this talk is basically the objectives of train but verify, which are eventually where we want to get is we want to be able to train machine learning systems to enforce more than one security policy. And we also want to be able to verify across policies. And for this particular talk, we're going to go through one of our recent outputs where we explore exactly what's happening between training to be defended against a do policy and then what kind of information that reveals. And then we're going to end the talk with an explicit ask where I want each of you, as we sort of run through this talk, right, to think about, from your perspectives, which are the off diagonals that are most important, which are the policies that you and your agency or your community are most interested in. It might not necessarily be do reveal, so happy to get that feedback at the end of the talk. So let's go ahead and get started with more the meatier piece of the talk. On the images that I'm showing you here are a movie of adversarial examples that are actually walking through the space. We've got a trained model, and then we went from airplane now to car, and then we're going to go through all of the other classes of CFAR10, and you can see the kinds of information that we're able to get out of these models, just at sort of interesting artistic level, right? And then on the math side, what is a sufficient condition for training a convolutional neural network such that adversarial examples against that trained model are recognizable to humans? That's the question that we're going to try and answer. The way that we're going to do it is we're going to go through a comparison of some of the state-of-the-art defenses. We're going to look at Madry's adversarial training, and we're going to look at trades and both of their approximate methods. And then we're going to basically state a lemma that we proved in our paper. And then we're going to go through some experimental results about whether or not the kinds of things that tie these methods together, specifically these gradient penalization methods, are sufficient for recognizability. And then we're going to close with a couple of thoughts on privacy. So let's get started. So if we're going to defend against do, it's useful to start off with what undefended training looks like. So the way that we normally think about this is that we are minimizing the expected loss, but not any particular further regularization. If you are, for example, going to train against, if you're going to try and make sure that you're not going to be fooled by an adversary, one thing that you might want to try to do is bring that adversary inside of your training process. So Madry's approach literally trains on adversarially perturbed stuff only. They get their training data, they allow an adversary to perturb it within a certain bound, literally allowing the adversary to maximize the loss, and then you try to minimize your loss after your adversary already had a shot at it. Another method called trades breaks it into two different pieces, where what we have is we have a term that is about the just standard training, and then we have a regularization term that allows the adversary to, again, mess with things. And then this method literally does, through beta, trade off those two concerns. Okay? And so looking at these, you might think that they're pretty different. Turns out that they're actually very similar. So let's go ahead and dive into Madry real quick. Since Madry's internal adversary, at least as we're writing it here, has that delta that's added to x, and delta is meant to be small because it's just an adversarial perturbation, that cries out for a Taylor expansion. So you go ahead and do the Taylor expansion, and then what you end up with is you again end up with two terms, at least to first order, where it ends up frankly looking a whole lot like trades, where you have a term that is about maximizing the accuracy as though it was an undefended model, and then a term that's about the gradient penalization. The way that the details of how you calculate this gradient penalization ends up connecting you to a bunch of different methods like Ettman et al. And Finley and Oberman and Roche and Doshi-Velez. But the high level piece here is that what you're doing is that you're penalizing the gradient. And you can see pretty quickly here, and we go over this in the paper, is that as you're penalizing the gradient, what you're actually doing is you're driving down the local Lipschitz constant, right? You're smoothing the model. So you're not only making the model, you're not only concerned with how accurate the model is, but also how smooth the model is, right? And so that's more or less what Madry and those approximate methods are doing in a nutshell. So what's trades doing? Turns out that trades is basically doing the same thing. One way that you can see this is you can plug in for the loss function, cross entropy loss, which can be written as an entropy term and then a KL divergence term. And then if you throw that into the maximization, you can immediately recover the piece that Miyamoto et al. Studied in their virtual adversarial training paper, connecting trades and VAT directly. These were, of course, proposed in different ways. But this is a direct connection to the actual mathematics behind them. And then if you start with that, what you can do is you can then again do a Taylor expansion. And when you do the Taylor expansion, what it ends up you're doing is you're actually maximizing the Fisher information matrix. That is in fact a Rayleigh coefficient. So it's just the largest eigenvalue of the Fisher information matrix that you end up driving down. So to back up, instead of penalizing the gradient like Madry is doing, what you're doing is you're in some sense penalizing the Jacobian, which is represented here as the largest eigenvalue of the Fisher information matrix. And again, depending upon the particular method that you use to estimate that eigenvalue, you come up with a variety of different methods that have appeared in the literature for making these kinds of models more robust. All right. So what we've done is we've connected all of these methods in some concept of smoothness, right? Madry, trades, and all of their approximate methods are in some sense smooth, right? And so what you can see here, we're just showing you a picture of trades. This is the half moon data set where you have sort of an arch of blue and then a valley of red. And on the left, you have sort of the standard way that you fit these models, or just a standard neural network, and you recover a nice boundary in between them. And then if you start at a point and then make adversarial perturbations following the gradient, they end up making those nice little trail structures, right? Then if you increase the regularization, you can see that this is getting smoother. Things smooth out a little bit. They just, I mean, I'll say it again, they smooth out. And specifically what they're doing is it's driving down the local Lipschitz constant. This is a limit that we prove in the paper. And if you over smooth them, you approach linearity. Okay. So now that we've done a little bit of a deep dive into the mathematics, let's come up for air and let's look at some experimental results. Is this kind of smoothness that we've outlined a sufficient condition for recognizability? And so to do this, I'm just going to show you some pictures and argue that it is in fact a sufficient condition. But before I do that, the thing that I'd like to show you is I would like to show just an evaluation on the do policy, because each of these defenses have in some sense differing degrees to which they work. The standard method and a historical defense called defensive distillation essentially provide no robustness against the adversary. They both tank really fast. What comes up next is the approximate methods in terms of the gradient penalty and the Fisher information matrix penalty. And then finally, we have the full methods, which include trades, Madry PGD, and also FGSM, which you can think of as a single-step version of Madry PGD that happens to just be particularly fast, right? And so what we can see here is that the robustness falls out depending not on whether or not you're doing a first-order penalization or a second-order penalization, such as you might think. Instead, it falls out saying that the approximate methods are not as robust as the full methods. All right. Now that we have a general idea of how robust these things are, let's go ahead and look at those pictures. So here, what we're looking at for that standard model up front is, again, we have a model that's just trained in the standard way. We're minimizing the expected loss over the training data, and then we're calculating an adversarial example that's targeted for a particular class, where the first class is airplane and the last class is truck, right? These adversarial examples that we're generating for the standard model may have patterns in them that if you knew a priori that, for example, that was a bird, you might begin to see a bit of a rooster in there. Or if you knew that that was a ship, you might begin to see a bit of a sail, right? But they're not particularly recognizable. If you use that other method, defensive distillation, which is a historical method that doesn't provide a particularly much robustness, right? You begin to see a little bit more of those patterns. And the reason that you see that is because a defensive distillation, defensive distillation uses temperature scaling to smooth out the model, right? And so we're beginning to see a little bit more of a signal as the model gets smoother, okay? And then if we look at the approximate methods, again, these things look more and more recognizable as we're sort of moving our way up the robustness scale. What's interesting to me, at least at a qualitative level, is that we're no longer looking at some smudgy averages of gray pixels, right? We're beginning to recover the particular colors that are notable for the particular classes. And then when we move to the full methods, we again see even more recognizable examples. For example, the deer in PGD looks almost like pixel art that you would download off of the internet, as does the ship in FGSM and a couple other examples, right? We're really beginning to get recognizability in these adversarial examples. Okay, so hopefully what I have done here is I have convinced you that this kind of defensive regularization is a sufficient condition. If you have that kind of regularization, either approximate or otherwise, you end up with recognizable models. So now let's go to revealing characteristics of the data collection. Let's begin to use these results in a novel way. So I have previously talked about adversarial walks just a little bit, talking about them as a sequence of adversarial examples. I want to walk through that more specifically so that I can set you up to understand some of the cool fine art stuff that we're going to put together. So imagine here that we have this very simple two-dimensional classification problem where we've got circles, triangles, and squares. We're going to just start in a random place. Turns out that we ended up in the blue. And so where we're going to head is we're now going to generate a series of adversarial examples towards the target class of triangles. as we move forward along the gradient, we generate an adversarial example, and then eventually we cross over the decision boundary, and now the model will recognize that as a triangle, and we keep on going. Then what we can do is we can change the class to a different class. We can go to the squares, and then we can go back to the circles, or we can kind of do whatever we like. And we can walk around the space without access to the data. We can just sort of see what the model thinks are typical examples by generating adversarial examples against the model. And so here's really what we were doing when I showed you that horse example at the beginning of the talk, where what I started with is we started with those horses, and then we walked them towards the deer, and you can see that those are the deer images that I had in the prior slide, and then we walked them back towards horse, and then that's how we got those pictures of the riders. So that what we were doing was an adversarial walk. So what else can we do with adversarial walks? This is what I like to think of as fine art, where what we're doing is we're doing an adversarial walk on an ImageNet classifier that's been robustly trained. And we've set it to music. Okay, and I'll just go ahead and leave that going, even though I'll kill the sound so I can still talk. What you'll see here is that you do in fact end up with adversarial examples that have characteristics of the data in them. So what are some things that you can learn from that? For example, if you do a adversarial walk towards the Stingray class, what you will notice, and keep in mind, this is without access to the data. We have no access to the data here. We started at a random start and just sort of moved around the model. What you'll find here is that we do get something that looks a lot like a stingray, and then we get something that looks a lot like a person who's swimming in the water with the stingray, right? And so you might wonder, I wonder how often swimmers appear in the stingray class. Well, if you download ImageNet and you go to the SYN set that represents the Stingray class, and you just look at the first 9 images, you will in fact see that there is one in those first 9 that has a person in the water. Looks like he's about to give a kiss to the stingray, which is not my idea of what I'd want to do on a vacation, but to each their own. Similarly, if you go to the cauliflower class, you'll notice that you get purple cauliflower. And I remarked to John, my co-author on this paper, John, what's up with the cauliflower? Cauliflower is not purple. And John's like, yeah, cauliflower is totally purple. Don't you ever subscribe to like a CSA or something like that? And so, truth be told, you then go to the SYN set for cauliflower, and you again see that there are examples of purple cauliflower in the first 9 images. Right? So this is the kind of information that you can get out of a robustly trained model. We also have examples of this kind of attack that works on what's often called black box, or what I like to call query-only access, where you only have access to query the model, but that work is still ongoing and moving forward. Okay, so what did we do in the talk? What we did in the talk is the top of the line thing that I want you to lead with is that state-of-the-art methods for training for do policies, right? To make sure that it doesn't do the wrong thing when presented with an adversarial example, leads you to have reveal policy violations, right? You end up revealing stuff that you wish you perhaps hadn't revealed. And also that enforcing do and reveal simultaneously will in fact require new methods. And that's why I've sort of put back up the train but verify grid and then claimed some space on it where we have a new row that's about enforcing both do and reveal, as well as laying out the particular cells that train but verify is interested in at the moment. And so what's our roadmap? We're going to do a lot more work on quantifying attacks to reveal policies. What I've done so far is mainly just showing you some qualitative stuff that perhaps an analyst could stare at and draw some conclusions on, but nothing that you could turn into a graph. Like, what is the robustness versus its revealingness? Those are the kinds of things that we're going to chase down. We're also going to develop new methods for do defenses and do attacks with an eye towards eventually getting towards methods that do both do and reveal. And we're also going to develop some new methods to verify do policies more efficiently so that we can more efficiently use them against reveal policies, right? Where we train to reveal, not to reveal the wrong thing, we can also more quickly verify that they won't do the right thing, do the wrong thing either, right? And then in FY 2022, we will in fact go after methods that enforce both do and reveal or trade off between those concerns. Okay, I'd like to thank all of you for coming. I'd like to thank my team, which includes both SEI folks as well as several professors on campus. And we'll now open the floor for questions.
Thank you for joining our Q&A for Train but Verify Towards Practical AI Robustness. My name is Tanisha Smith, and I'm a technical manager with CMU's SEI Emerging Technology Center. I have John here. John, would you like to introduce yourself?
Yeah, thanks, Tanisha. I'm John Helland. I'm a machine learning researcher in the Emerging Technology Center here, and I've been working on the Train but Verify project with Nathan, and I'm happy to answer any questions.
Mm-hmm. Awesome. Okay, so let's see what questions we have. It looks like, okay, first question, John. How might this be applied to other input domains like audio or text?
Yeah, so the context of this presentation has obviously just been kind of image perception, and the problem of applying it to other domains, I mean, obviously depends on the specific domain. So if we talk about audio waveforms, the models that you might usually use for audio waveforms take a different form than the models you use for image recognition, which would just be a convolutional neural network, just a feed forward model. In the context of audio waveforms, you would have a recurrent neural network, so there would need to be some additional thinking done about how you would kind of translate this technique of generating like input images in that context. In a discrete domain like natural language, you might have models that are a little bit more immediately applicable to this context, but then you have the problem of kind of discrete inputs that you need to map back to rather than a full continuous space. And we think about images in the full continuous space. So you could do something like basically take the model after the embedding layer for an NLP model, and then maybe you could compute gradients with respect to that version of the space, and then you could do a sort of nearest neighbor thing with respect to the collection of natural language tokens that you have. But yeah, it's not really a resolved thing. It's not something we've looked into, but I think it would be definitely interesting to consider other domains.
Okay. It looks like actually we got another question. Does this attack also suffer from mode collapse like generative adversarial network models tend to do?
Yeah, that's actually pretty interesting. So I have noticed some things that are kind of similar to mode collapse. So if you just take your initialization of an adversarial walk as random noise in the space, you run into this problem of the noise being classified as just kind of one particular class. And then when you actually pick some other class to perturb towards, then you end up kind of getting outputs that all look the same because you've started in kind of the same region of the space in some sense. So that's one part of the problem. And there's another part of the problem where it seems as though methods of adversarial training end up kind of focusing on one particular class over the others to kind of defend against. And so by that, I mean, you have this idea of the adversary performing perturbations on the input. And it seems as though the model can oftentimes learn this sort of mode collapse type behavior where it tries to sort of learn weights so that when you compute the gradient, it kind of shoves all of the perturbations into one small section of the space. And so then your perturbations all kind of tend to look the same. So that seems to be two versions of what you might consider to be mode collapse.
Mm-hmm. Makes sense. I think we might have time for one more question. This one is around recovery images. How closely do recovery images match up with training data?
Yeah, so in the context of like a convolutional neural network, you have this property of convolutions that would be like spatial invariance. So it's kind of interesting when you're trying to change pixels so that it maximizes a certain output of the network. Because of that spatial invariance, you can end up sort of creating features in various parts of the image. So you might end up with multiple dog faces like dotted all over the image in this kind of weird deep dream looking thing. And so because of that spatial invariance, it's kind of a difficult problem actually to solve how you would actually directly compare these adversarial walk outputs with the original training data. You could go in manually and create masks and then compare those masks to things that you know in the data set, or you could try and do something like GAN literature, like Fouché inception distance or something. But yeah, it's difficult to do it in a principled way, I would say. So that's something that we're kind of interested in thinking more about. But for now, we just kind of have qualitative measures.
Okay. I think we've just run out of time. Thank you so much, John, and thank you everyone for joining us in this session.
Yeah, thanks, Tanisha.
Good afternoon. My name is Ed Morris, and I'll be speaking today on a 3-year line project called Video Summarization and Search. I've also asked Adam Harley of CMU to discuss his contributions to the work. The problem we're trying to address is that aerial surveillance demands full attention of small teams called tactical PED teams with 3 to 5 people. They are on the job 8 hours a day and 3 shifts per day, obviously, to fill the 24-hour period. It's a manual process. It's error-prone. Analysts get distracted. They may be focused on the wrong areas, and many other things can happen. In addition, the changeover between shifts is very problematic. There are also technical barriers to providing good tooling for them. Our technologies for object detection are not as good as they should be. Once we detect an object, we can't recognize it consistently as the correct object, and finally tracking those objects is very hard. These limitations result in poor pattern recognition in a surveilled region. And of course, pattern recognition is what they really need to do. They don't need help necessarily identifying things as much as they want to find the bigger patterns. Our approach is twofold. We're working with DoD in pattern recognition technology for aerial surveillance data. And second, we're working with CMU researchers to address core technology problems associated with object tracking. We have several achievements to date. First, we've been influential in DoD pattern detection strategy, and we're currently serving as a reasoning pathfinder for DoD. Reasoning is their word for pattern detection or pattern of life detection. Our 3D tracking research is also achieving state-of-the-art performance. Our products are source code that's primarily available to DoD, and also publications that are in the public literature. Once again, we're currently involved in 2 activities. First is support to DoD, and second is the research. in terms of transition, we're doing several things to make the DoD capability for tracking better. First, we're removing dirty data from the aerial camera data. There is a lot of dirty data in camera data. First, the values of the onboard sensors for lat and long could be incorrect. And second, the platform drift itself often leads to spurious detections or missing detections, and certainly leads to bad downstream tracking, and for other apps as well. Our approach then is to clean and smooth the data prior to downstream processing. First, we can apply moving median smoothing techniques to kind of get rid of the unrealistic jumps in speed and location that occur in the data streams from these platforms. Second, we can correct some bad geo registration locations. The two images on the right show an example of that, where the blue boxes are fixed and we know where they are. The red boxes initially on the image on the left are the lat long location that is given to us at least at one point for those two boxes. The reality is in black. And after our geo-registration strategies, we have now located them in the correct spot. Third, we can apply Kalman filtering to reconnect tracks that have been dropped or correct tracks that have been switched. We can also improve lat long with that strategy. A second thing we're doing for DoD is statistical reasoning about this aerial surveillance data. Keep in mind that most activity is normal and not harmful at all, but some of it is. We can use our statistical pattern of life detection capability to map out what's normal in terms of a location that's being surveilled, detect anomalous activities that potentially could be bad, and ultimately search for those activities in a data stream. The implementation is pretty straightforward. We separate the region into grid points based on camera attention. We remove the bad tracks. We calculate things like mean speed and heading and density within that data, and then we can detect anomalies based on a set of rules we set for what is considered inappropriate speed or inappropriate heading. The examples on the right show that. The top example would be what the tracks look like coming out of the data. The example on the bottom shows what happens after we do our statistical reasoning, where we now have identified things that are moving fast, obviously on a roadway, and things that are moving slow. A third thing we're doing is we're applying anomaly detection, machine learning based anomaly detection strategies. What this basically is applying an LSTM, or long short-term memory autoencoder to observe a set of tracks. From that observation, it begins to understand what's normal effectively. Now, when you provide other tracks to it, it will say, well, if it can reconstruct those tracks based on what it knows, it considers it normal. But if it can't reconstruct those tracks, in other words, there's a high reconstruction error, then they're identified as anomalous. The image on the right shows an example of this in action. This data was actually perfect data coming from GPS devices in cars for a DoD exercise. On the left, in the green, with the green dots, those are presumably individual cars on a roadway. The tracks are not shown here, by the way. That's a perfectly normal pattern of activity. However, the anomaly detector was also able to detect two vehicles that met on a little used road in this exercise. Now, whether that's important or not, of course, depends on the mission. And I want to point out again that this was perfect data. This is not necessarily what you would see with an anomaly detector applied to the tracking capability we have now. So what are the barriers to progress? Well, poor object tracking, which I've talked about, is certainly one of them. And there are several reasons for this poor performance of object tracking. First, the current state-of-the-art in object tracking uses 2D camera frames and then identifies objects across frames and relates them. Well, the problem, of course, is that objects look different depending on the viewpoint. A car from the front looks very different than a car from the back, so it's very easy to throw off the object detector and recognizers. Second, any kind of occlusion throws off 2D tracking techniques quite a bit. Even partial occlusion, going under an overpass or being hid behind a tree, can throw a tracker off significantly. Third, the coordinates in the frame are not necessarily good enough for you to predict where that object will be in the next instance. The example on the right will show this. I'm going to start up this video now, and you can see that the people walking are, even though we know they're walking a straight path, their location within the frame is not what we would expect based on a straight path. It's actually moving based on camera motion. There's a secondary problem too, and that is the best performing tracking algorithms require many images in order to train to detect those objects. But the reality of DoD is you often have very few images. For example, if there's a new missile launcher platform that an adversary has deployed, we are unlikely to have a lot of images of it. We may have some. We're very unlikely to have enough images of it from various perspectives to be able to recognize it in many different situations. In addition, there are many cases where analysts are looking at the images or the video coming in, and they may not know what the object is, but they do want to track it. So you need to have a capability that allows you to do that. The result is, once again, poor identification of objects, lost tracks, and poor pattern detection. Our strategy for addressing that is we're collaborating with Adam Harley and Dr. Katerina Fragiadaki from the CMU campus. Adam has done a fantastic job and has turned this work into the focus of his PhD thesis, and I'm going to let him take over at this point. Thank you, Adam.
Thank you, Ed, for the introduction. Before I get into the work itself, I'd like to motivate it a little bit more with the help of these videos. So what we want to be able to do is take a video like this one as input. This is a video captured by a drone looking down at the ground, and we want to be able to produce as output detections for all of the objects of interest and also tracklets for those things, which just means drawing on a map where we think those objects moved over time. And we're going to be talking about models that do this with the help of 3D information. And it's useful to say why we care about 3D. And one of those reasons is that it actually makes the job easier, meaning it makes detection and tracking easier. One way that it does that is by stabilizing the data. And so, for example, here, stuff that was stable in the world is now suddenly stable in the video. And that's a nice thing because it can make things that were initially complex into things that are now very straightforward. Like this trajectory over here, for example, while it was a little unpredictable in the original video, after you take into account the camera motion and sort of cancel it out, then suddenly it's just a straight line and it's a person walking along a fence. So the hope is that if you take into account the 3D geometry of your domain before asking a machine learning model to do any learning, then that model is going to generalize better than one that has to figure out the geometry and the problem of detection and tracking all at once. For the results I'm going to show today, it's mostly going to be on urban scenes like this, because that's the data that we have in academia. But in general, the same kind of method would work no matter where your camera is, because everything is 3D. So there are going to be 3 parts to my talk. First one is about tracking objects. The second one is going to be about tracking the camera itself, so that you can do the kind of stabilization that I was talking about. And the last part is on a model that proposes things that are worth tracking. And then the hope is that all 3 of these can sort of work together so that you propose objects to track, track them, and also improve the tracking or make the tracking easier by canceling out the camera motion. So for tracking objects, the main problem that we wanted to address is the amount of training data that you typically need to train a good tracker. So tracking labels are very expensive to obtain in the real world. And if we can reduce the amount of labels that you need, that's a good thing. So we tried to think of what are some other labels that might work just as well. And what we came upon is this idea of static point correspondences. So here I've got 2 frames of a video, and I've marked a couple correspondences. So for example, this little pixel over here is on a sign on a fence, and I can find that same pixel down here. If your whole scene is static, meaning nothing is moving except for the camera, then it's fairly easy to solve this these days. Like, you can just download an algorithm off the internet and produce tons of these correspondences. So what we thought is that it would be nice to use these correspondences from static points to be able to learn how to track moving objects. And the key insight, you could say, is that the features of these stationary parts of the world are going to be pretty similar to the features of moving parts. So all we need is something that can do the correspondences visually rather than rely on geometry, which is what the classic algorithms would rely on. So as output, you end up with something like this, where I've got the ground truth shown in yellow and the estimated boxes in blue, and accuracy is shown in the numbers. Also, to explain a little more, so this view up here is the camera's viewpoint, and this is a bird's eye view down here. Mostly this is successful, which is kind of incredible since we're not using any tracking labels. It's just those point correspondences. The boxes do jump around a little bit, but this is maybe understandable because we don't have any motion priors right now. All we're relying on is these frame-to-frame point correspondences. And we're able to show that this works not only in a simulator, but also in real-world videos. Quantitatively, it looks good also. So in this plot, I have all of the supervised models, or sorry, the self-supervised models are in solid lines. So ours is in black up here, and it's a good margin above the rest. The supervised models are in these dashed lines. And you can see that in the harder data sets, especially as you track for a longer period of time, you are better off using a supervised model, but we're not too far off. So the main idea here is that we show that if you learn correspondence from static 3D points, then 3D object tracking will emerge. The second thing is, in the paper that corresponds to this, we're also introducing a neural 3D mapping module, which is just our 3D neural network. And this simplifies prior works trying to do similar things for 3D inverse graphics. We also, in this paper, introduced a method for training for correspondence in dynamic scenes, which people haven't been able to do before. And our method here is very simple. All we do is, if a video has dynamic parts in it, we manage to just discard those moving parts and only train on the static portions. And it turns out this is an important thing to be able to do, to be able to train on real videos. So that's part one, about tracking objects. And here I'm going to talk about tracking the camera itself. So our method for tracking the camera is actually pretty similar to how we track for objects, in terms of we're going to have something from some reference, which in this case is going to be our map that we're building over time. And then we have some new input that we want to localize with respect to the reference. And we specifically turn our map into a 3D feature tensor, similar to before. And we also turn the current frame into a 3D feature tensor. And then we do our cross correlation. So this is, as before, just doing a lot of dot products at different spatial positions. And then we turn this into a rigid transform, just like for object tracking. But in this time, we're doing all of this in a loop, so that we're able to add to the map and make it more and more dense over time, and that makes this model into a recurrent thing. So overall, just to have a clean takeaway, we're taking as input RGBD videos here and producing as output the rotation and translation of the camera as it goes through the scene. So I've got qualitative results here. This is the RGB of the video going into the model. And here on the bottom is the map that is building over time. So you can see that this map is getting denser and more complete. And also you can see that the red trajectory is our model's estimate, and the green trajectory is the true one. And these are pretty close together. This is an important step for us because we want to be able to always localize the camera with respect to a map, and we want to use that to be able to stabilize videos, like I showed at the very start. But quantitatively, it turns out we're still actually far from the traditional methods in this domain. So we're able to show that the things that we're adding in terms of map building and this course-defined refinement, they do help us reduce our error, but OrbSlam 2 stereo is just a phenomenal method. So we're still trying to beat that. In general, though, we're working here on a neural ego motion module in terms of, ego motion, I just mean camera tracking. And this is capable of map building, which is kind of a unique thing for a neural network. And gradually we're closing the gap between the deep and so-called traditional methods by essentially doing what those traditional methods are doing, but in a neural model. So we're hoping that this is going to pave the way for a more general system that is maybe more closely linking the two, and it's also going to work in the domains where the handcrafted methods fail. What I want to show here is a method that can propose objects and then track them all on its own. So no human intervention at all, just deploy this thing and it's going to find things and start tracking them without any supervision or intervention. So this is useful for if you don't have good detectors for the thing you want to track, or also if you want to be able to track without a human in the loop. So here I've shown on the left the input to the model, which is going to be an RGBD video stream. And similar to before, we're going to be creating 3D estimates of the scenes depicted in these frames. So I've shown these volumes here, and again, inside each inside each cell of the volume, we have a vector that encodes some semantic content. The key operation here is a median followed by a subtraction. So first of all, when you take a median of all of these volumes, a median over time, you end up with an estimate of the stable part of the scene, which corresponds to the background. And then when you take a difference from that median, you end up with an estimate of what's not background. And in other words, that's going to be mostly your objects. I can show already what that looks like. So given this video on top, the median is over here. You can see it's perfectly stationary because we take one median, no matter how long the video is. And down here, I've got the differences from the median. And what you should see here is in a bird's eye view, we've got a bike over here and a car coming down, coming from the bottom. So the important thing is that the big white blobs in the bottom here in the difference map correspond to actual objects in the video. And we have a process also that's able to select these blobs and sort of sort them big to small, and then start to track them. And essentially we just use the method I showed in the first part of the talk to be able to do that tracking. So in this bottom right column, bottom right part of the slide, I'm showing what those tracklets look like. So it's really that simple. Given an RGB video, we'd find 3D median and then take differences against the median, and that's your objects. So we've shown that object discovery is surprisingly easy if you appropriately exploit the geometry of the scene, and also, of course, if you have access to high quality information about like depth and camera motion. And the nice thing about this compared to previous object discovery methods, like ones that try to do discovery based on optical flow, for example, is that here we're using very long time horizons, which seems to be much more reliable signal than these short time horizons. So that's all from me. Thank you.
Thank you, Adam. Just to briefly summarize, we offer transition support of the work we're doing to DoD, and in addition, we support research on 3D tracking. Our next steps are to continue to work with the DoD to improve pattern recognition for aerial surveillance data, and of course to continue the 3D tracking work of Adam Harley and the CMU team. Thank you all very much. Are there any questions?
Good afternoon. I want to thank each and every one of you for attending the research review, and in particular this session. I'd like to start out with a question for Adam. Adam, what are the major advantages and disadvantages of your approach compared to other approaches that are based on trained object detectors?
That's a great question. I think that the main disadvantage of using a pre-trained object detector is that there's a built-in assumption that that detector is going to work when you try it on your test set. And that's a tricky assumption to make because you don't really know how different your training distribution is going to be from your test distribution. So what my approach is trying to do is get rid of that assumption by allowing us to do some self-supervision in the test domain. So if you're able to improve your trackers, improve your detectors just by using free labels that you can acquire from like multi-view data or optical flow, something like that, then I think you're more likely to do better on the test set. So the main benefit really is generalization, I think, from my approach compared to using some pre-trained object detector. Maybe I can ask you a question, Ed.
Sure.
What more is needed to make a more sophisticated pattern recognition system possible for aerial perspective systems?
Wow, a whole lot, actually. First, we need more and better object detectors, as you could expect. Right now, we're at the point where we're doing the fried chicken situation. We're in the fried chicken situation where our current object detectors can sometimes detect things like, or classify things like explosions as fried chicken. And that's the reality, even for large objects from aerial perspectives. We also need to understand much better who the people are that we're seeing down below, if we're seeing those people to start with. It's not enough to say there's a person down there, but we have to know whether that person is a man, woman, or child. We also have to know whether that person is armed or not. So once we do that, there's still a lot of work to determine what particular weapons or other supplies are available on the ground. Now that's just the detection of the objects themselves, but the bigger problems or the bigger benefit actually comes later on when we can actually detect patterns. For example, you can imagine a situation where there are barrels of what look like to be industrial chemicals, there are agricultural products and there are fires burning. Well, that represents a pattern that may be the processing of drugs or the creation of heroin from poppies. Another situation where there are unusual delivery of crates at various and unusual hours, specifically sized crates, and it may be patrolled, the area may be patrolled by armed men. In that case, it may be a weapons cache or something like that. And that's the type of the pattern over the longer term we have to be able to understand. But there's more still. It's not just that we recognize those patterns in an instant, but those patterns appear over time. The crates can be delivered one day. The armed guards appear later. And in terms of the barrels, they may be delivered one day if it's a drug processing situation. So the point is we need a history of those things, and we have to recognize the pattern occurring over that period of time. And that period of time could be quite long, actually. So once we get beyond the point of the history, there's still the relationships to other forms of intelligence. So for example, we may want to know, it may be very useful for our focus of our pattern detection to know that an informant, for example, suggests that there's some activity going on in a specific area, or that a number of armed unknown men have appeared in a particular area. So all of those things are important to know, and we're not nearly there yet. To kind of close, the value of all of this work will come down the road. It's not going to be immediate, but there is a lot of work that has to be accomplished before we get there. Thank you all very much. I appreciate the time that you've given us this afternoon. Thank you.
Maybe I can quickly ask.
Hello, I'm Carol Smith. I'm a senior research scientist in human-machine interaction here at the SEI, and I'm going to be talking about ethics in AI engineering. Our document markings, and let's get into some background about ethics. So ethics are based on well-founded standards of right and wrong. They're the standards of expected behavior that guide our correct course of action. And according to the Defense Innovation Board, ethical considerations are an inseparable part of research design and deployment for DoD AI systems. Here at the SEI, we look at the AI engineering process and all the aspects therein. And part of this is the work that needs to be done on a continuous basis around data management, algorithms and models, operations, and governance. And within governance is ethics. Ethics are how we ensure that the team is making the system accountable to humans, that the team is cognizant of speculative risks and benefits, that the system will be made to be respectful and secure, and that it will also be honest and usable. And AI does have great potential, but we need to continue to develop it with caution. Many years from now, AI may be a trustworthy substitute for human cognition and abilities. However, for moral and legal purposes, humans must continue to deliberate over situations that involve a person's life, such as the use of force, their quality of life, their health, and their reputation. The Defense Innovation Board has said that the AI will ensure appropriate human judgment, not replace it. So why are ethical principles for AI important? Ethical principles improve consistency. The team that has a diverse set of ethics coming into a project can coalesce on a shared set of technical ethics. And the principles will help to harmonize the cultural variations that those team members have across the group. Ethical principles can also aid in achieving a number of other aspects, including building on existing ethics that the organization has, but really specifying them for the technical problems they're trying to solve. Being able to balance to the pace of change. Industry pressure is often very fast and pushing for quick releases, which is not a bad thing. However, we want to make sure that we're really thinking about all the implications of the work that we're doing, and ethics give us that framework to do that. They also help to provide expectations and explicit permissions to consider and question the breadth of those implications, and to encourage the team to really think about what they're trying to do and why, and what those potential implications are. So who are they for? They're really for the entire team. Everyone creating an AI system should be using technical ethics to ensure that the work remains human-centered. Data scientists and data creators, product managers, machine learning experts, programmers, system architects, and what I like to call curiosity experts. This is the collection of people who focus on situations, users' abilities, and the context that they're doing the work in. These people can activate curiosity via user experience activities, and they usually have titles such as UX researchers, human-machine interaction specialists, or human-computer interaction practitioners, and digital anthropologists. Bringing this whole team together requires early, purposeful work. The team's efforts need to focus not just on the algorithms, although that's a very important part of ethical work, but also about the conduct, the interactions, and the intent and how the system will maintain appropriate levels of trust with the users and the people that are affected by its use. We need to work on efforts to reduce risk and unwanted bias and consider the benefits and the harms to individuals with these systems. So, for example, thinking about what is going to happen with the system initially, and then how does it change over time? Does it change? What changes about it? Can harm be mitigated? And are those mitigations potentially going to require a trade-off against a benefit of the system? And what is that benefit that we might lose? We also can speculate about misuse and abuse, focusing on the potential severe abuse and consequences can really help us to understand the range of situations that might occur, but also understanding those concerns and fears of people who are affected by the AI system can help to identify potential misuse and abuse. So really thinking through all those variations, not necessarily the breadth of them, but the most extreme ones within those situations. Now, to be biased is to be human. Biases are shortcuts. They're ways that we can avoid risk and simplify problems, and they have helped us to be successful as a species for thousands of years. They are not inherently bad, but they may be misapplied. they're implicit or invisible. We're not always aware of them, and they're not necessarily in sync with our conscious beliefs. So for example, if I see someone in my neighborhood and I think something negative about them, that might be my bias, my inherent bias. And I can think through that situation and realize that that person probably lives in this neighborhood. I just haven't seen them before. Or whatever the case may be, I can think through that and change my response and change my thinking about that. And that's the good thing about biases. They can be managed and changed. We can talk about these biases in non-threatening ways to be productive and move forward and to realize what we need to change about the way we're thinking about people and situations. So bias is intrinsic to our experiences, and it comes from many, many different experiences that we've had, such as the social class we grew up in or the social class that we're currently in, our resource availability, our education, our race, gender, and sexuality, as well as culture, theology, and tradition. All of these things and more can contribute to creating the biases that we may bring along with us to our work. And we often have no way of knowing when and why people are biased. Sandra Wachter talks about this. She is a fellow at the University of Oxford, as well as the Alan Turing Institute. And this is an important thing to realize, is that since we don't know what people are thinking, we may not know what the system's biases are either. And so we need to realize that all systems do have some sort of bias. The idea of complete objectivity is misleading. Math and algorithms don't remove the bias that humans have instilled in the data and the systems that we create. Bias can have purpose and it can be helpful, but we need to be aware of it. We need to recognize it within the systems. So our goal needs to be to reduce unintended bias or harmful bias and prevent the inevitable harm that comes with unknowable systems. We need to understand these systems and know how they're affecting people and know how they're going to behave within the realm of the work that we're doing. So bias can enter from a variety of different sources, including the data source. This is the most common source of bias. Because data is created by humans, it is inherently selected and curated by someone with a certain bias. They're thinking about doing work in a certain way. And the way they curate and organize that research or that data is going to change the way that data can be used in the future. Algorithms, of course, as well, and we've seen this through the racial bias and race and gender bias in a variety of different systems that have been created based on, in many cases, biased data sources themselves, but also potentially selecting an algorithm that will result in a bias. And then training. Training can be purposeful and towards a particular outcome, a more aggressive treatment for a medical situation, for example. But it can also be inadvertent due to the content or due to the understanding of the person doing the training. If you're doing an individual training and those individuals have specific biases, they can instill that in the system. This is new and uncomfortable work for many people. They may not have the background or the experience dealing with these situations, and we need to get used to being uncomfortable. Laura Kabag talks about this. She's an author and designer, and she talks about how ethical design is not superficial. It needs to be done very carefully and intent. We need to use intent when we do this work to make sure that we are doing the right thing, that we're making decisions that we mean to make, and that the system is going to work in the way that we intended to. We also need a diverse, talented, and multidisciplinary team. And this group needs to bring their varied skills, problem framing approaches, and knowledge together so that we can really build great systems. And when I say diversity, I mean diversity in a lot of different ways. So this includes, of course, gender, race, and culture. But this also includes education, their school and their program. For example, if everyone goes to the same school and takes the same course from the same professor, they are likely to approach problems in the same ways, and they will also miss the same issues potentially. So we want that diversity of experiences and thinking processes, age, disability, and health statuses, and more. All these different experiences come together to help us build a great system because great minds think differently. We're not lowering the bar here. We're talking about extending it, making a broad group of people come together to solve problems together. And this is partially because diverse teams mitigate bias. because they focus more on facts, they process facts more carefully, and they are more innovative. Harvard Business Review published a study last year, and they found that they become more aware of their own potential biases, and they entrenched ways of thinking that could otherwise blind them to key information and even lead them to make errors in decision-making processes. So they're aware of these issues, and they use that awareness to help make sure that the work that they're doing is better, which is wonderful. So our grand challenge is to make ethical AI. Here at the SEI, we really want to work with individuals who are interested in doing this work and to help you and to help us all have systems that we can trust at a reasonable way and that we feel is doing the right work. The Department of Defense has adopted ethical principles for artificial intelligence just earlier this year, and we want to take these ethical principles and transform them. But how do we do that? How do we take ethical principles such as responsible, equitable, traceable, reliable, and governable that the DoD has adopted and transform them into trustable ethical AI? There's some steps involved. We do have some guidance already developed, but we need more. So one set is our 11 foundational practices of AI engineering. And this includes the ideas such as treat ethics as both a software design consideration and a policy concern, incorporate user experience and interaction to constantly validate and evolve models and architectures as well as users' experiences, and designing for the interpretation of the inherent ambiguity in the output. How do we make these systems understandable to people? These are all aspects that we need to consider as we move forward in making AI engineering ethical. We also have the SEI checklist and agreement, and this is to be used to prompt conversations for understanding. This is not meant to be a checkbox where you just go through the paces, but rather the start of the work that you need to do. This will help you to test the application of ethics, to reduce risk and unwanted bias, and to support the inspection and mitigation planning that needs to become a constant part of making these systems functional and safe. This is part of the framework for designing trustworthy AI. The checklist came out of these 4 aspects of that framework: accountable to humans, cognizant of speculative risks and benefits, respectful and secure, and honest and usable. And there are a variety of different prompts inside the checklist that, again, are going to help your teams to reveal hidden tasks, work that they still need to do. So it's not as much of a checklist as a way to measure the work that needs to be done. And examples such as humans can easily discern when they're interacting with an AI system versus a human. Is that ready? Is the system been built in such a way that they can discern the difference? And if not, what needs to be done to make sure that that is true? So thinking through that and having those conversations is really important. Teams also need to create communication and mitigation plans, so they need to plan for those unwanted consequences ahead of time so that if they occur, when they occur, they can react in a reasonable way. This includes thinking about who can report an issue with the system and who do they report that to. What is the method for turning the system off? This is really important. And also, once it's turned off, or who has access to turn it off, but once it's turned off, what are the consequences of turning it off? Who's notified? Is there another backup plan, a way that people can continue to get their work done even though the system is no longer working? By thinking through this ahead of time, you'll be ready for situations that may come up. And of course, these conversations for understanding, sharing information, sharing knowledge, and really querying each other and making sure that we all understand what we value, who could be hurt with the system, what lines won't our AI cross, and how are we shifting power? Who is gaining power? Who is losing power with the use of the system? And most importantly, how do we track our progress? How do we know that we're being successful in making ethical, trustable systems? One interesting activity is to reward team members for finding ethics bugs. So really investing the spirit of this work into the team with benefits. Dr. Ayanna Howard presented this when she was on the Artificial Intelligence podcast with Lex Friedman, and she has some other really good ideas for really getting teams excited about this work and engaged in it. We also want to think about how we're going to mitigate the bias that we may be in the system. Part of this is just reviewing the data, thinking about who created it, who organized it, who curated it, how was that done, were respected experts in the area involved in that creation, and what bias does the data already have. Also think about the system training. We need to engage potentially a diverse team, ideally a diverse team, and making sure that they're being mindful of the bias though, and their own bias as well as the system's bias. And making sure that we understand the approach that's being used for that training and that it's appropriate and that it's going to minimize any additional bias. We also want to activate curiosity, and we can do that by incorporating user experience research and human-computer interaction methods to activate curiosity. And these can involve a variety of different activities, such as having team members take the implicit association test that Harvard University developed. This is a way to understand better what your own biases are and to identify them. And once you know what they are, you can be aware of them and how they might affect your work. You can also try flip it to tested activities when you're going through various scenarios to make sure that you're not being overly biased in the way you're thinking about individuals, performing abusability testing of systems, and creating Black Mirror episodes. This is inspired by a British dystopian sci-fi series that has the same name, and if you haven't seen it, I highly recommend it for thinking through what those most severe abuses might look like of technology. Those potentially severe abuses and consequences exist, particularly for people who are frequently marginalized, and we need to make sure that we're thinking about those individuals, women, racial and ethnic minorities, LGBTQ. All of these individuals have potentially even more significant bad results from using systems, and we need to think about their experiences, particularly when we're designing systems. We want humans to remain in control and making sure that these systems are augmenting our experiences and augmenting our knowledge and not becoming a situation where we lose control. We want to ensure humans can unplug the machines. Grady Booch, an IBMer, has said this in his TED Talk, and that's the spirit of the work that we need to do, making sure that we are in control and that we know what the system is doing and why it's doing it as best as we can and as appropriate given the situation. So again, this grand challenge, we want you to partner with the SEI. We want to catalyze the community in implementing ethics in AI engineering. We want to develop activities to activate curiosity, speculation, creativity, and imagination. And we want to make sure that we're reducing ethical risks of systems. So making sure that potentially unwanted, unintended, and inevitable consequences are avoided. We want to create education and tools to support new and difficult work because we know that this is a huge challenge for some organizations, and we want to experiment to prove what is most effective. Please reach out and contact us if you're interested in partnering with us on this exciting challenge. Thank you.
Hello, I hope you found that helpful, and thank you for joining the Q&A session. Joining me is Alex Van Dusen. She's a design researcher, and I've had the pleasure of working with her on a variety of projects in the Emerging Technology Center here at the SEI. Alex, do we have any questions?
Yeah, hi everyone. Thanks, Carol. I'm really happy to be here. The first question we have today deals with who should be responsible for ethics. So the question is, do you think it is important to have a single person responsible for accounting for ethics?
That's a great question. And in the talk, I talked about everyone taking some responsibility, but at the same time, it really is important to have a single point of responsibility. Everyone should be participating in the work, but having that one person, a centralized role, someone who is ideally responsible across the organization so that they can manage trends and manage ethics in general, that's ideal. And also having individuals within those teams who can coordinate within the deeper questions. And this is work that takes time, and it's not easy work, but it is important to have people responsible so that it doesn't get assumed that someone's taking responsibility for it.
Patty Moore says, excellent presentation. So good work, Carol.
Oh, thank you. Thank you.
We do have another question. Is there a certain set of biases that you notice are particularly prevalent in AI for DoD?
Yeah, so there are definitely biases that we all have, unfortunately. Something that was referred to earlier this morning, autonomy bias, is the assumption that machines are smarter than people or that they can fix human issues. And that's a common situation where people just give too much trust. They trust these machines, these systems too much. And the opposite, of course, is a complete lack of trust, a distrust of the systems. And so ideally, we want to help everyone, help warfighters to get appropriate levels of trust and be reasonably skeptical of the systems so that they both understand the limitations as well as the capabilities of these systems and can work with them in a responsible way. As far as, real biases, patterns of biases, I haven't seen as much of that specifically. Certainly some of what has already been addressed today as far as recognizing images and things like that, where I'm thinking of the chicken, of course. The system is going to have situations where it's not going to be as successful, but I haven't seen specific patterns across the DoD. Unfortunately, the AI systems just can't fix problems that we haven't addressed as people yet, and they are limited in situations, but no specific patterns yet that are specific to the DoD.
Another viewer, Marie Francesca, says, thanks for your work in this important area.
Oh, thank you. That was very kind.
So, Carol, could you tell maybe our listeners and our viewers if they want to create a more diverse team, do you have some tips or anything that you might suggest?
Yeah, so it is always a challenge. There are lots of great, talented people out there, though. Some organizations and events that you can look out for are, there's an organization called Blacks in Cyber. They have a conference yearly. They just had one a couple months ago. The Anita B. Grace Hopper Celebration is generally an organization that has a huge amount of engineers, academic as well as industry professionals, primarily women. And then the National Society of Black Engineers, they actually just had their conference this past year in Pittsburgh, and they're another great source, places where you can advertise roles as well as just meeting individuals that you might not meet at other organizations.
Great. So previously you talked about biases, and we have a question from the audience from Patty Moore. Is there a list of specific lessons learned in the area of biases?
Actually, there are a couple of different resources, and I can get you those links after this talk. There is a GitHub repo that has listings of various poor decisions. I can't remember what the repo is called, but I can send out that list later. And there are lists of articles on ethical issues that are being compiled by a class, which I can also share that with you. Not a class I'm teaching. Casey Feisler is teaching that class at a different university, but I can definitely get you links of those and put those into the chat window.
So speaking of resources that might be available, Carol, you've worked on designing ethical AI experiences checklist and agreement. So could you explain a little bit about what you hope to achieve with that checklist and how you recommend it might best be used?
Yeah, so I'm really hoping that this type of activity isn't just used as a checklist and that people are just saying that they're yeah, we thought about that, but rather they're really having those conversations, getting deep into the thoughts about their work, being critical of their work, and really thinking about the ways that it could be misused and abused so that they can prevent harm, unintended harm to people, and to also to help make a better system so that individuals who are using these systems, the warfighters and others who are using these systems, don't need to try to memorize information, but rather can really use the system in a very productive way and a way that makes them feel confident in their work and that really augments their abilities.
So we have another topic on biases. We have another question from the audience. And they ask, can you talk a little bit more on using HCI to combat biases?
Sure. Yeah. So HCI is human computer interaction. And really part of that is understanding that there are people who are going to be potentially abused by work and can be because of the way the systems are built, because of the potential biases in the data, individuals can be harmed by the systems. And so understanding their needs, their perceptions, the risks that they're potentially having, and by doing that research to understand that, you can then mitigate that that effect. It's also just helpful in general to know who the people are who are using the system, and to think about people who you may not typically think about using the system as well. So there are lots of different ways you can use practices of human-computer interaction or user experience research to do that. And the other things are what I mentioned in the talk, are doing those types of activities, those curiosity, creative activities that really help the whole team to coalesce around technical ethics and to think about the problems that might ensue thereafter.
So a final thought, final question we have is, early in your talk, you speak about being accountable to humans. So would you mind elaborating more on that topic?
Yeah, and this was talked about earlier today as well by Dr. Cummings. It's really important that we make sure that humans are able to be responsible for decisions, particularly decisions where human life or significant decisions regarding a human's way of living or their safety or anything like that, that humans are involved in those decisions. And that's partially because we just need that accountability. And it's also because these systems are prone to mistakes, as are humans, and we need that secondary check. We need to make sure, is this really what we intend to do? Is this really what we are saying that we want to do? And that way, the system is, again, augmenting our abilities and augmenting our knowledge, and we are not dehumanizing people. Rather, we're really thinking through the situation and specific to the individual that we're dealing with. And just being fair and accountable is really, really important. Thinking a little bit more about that, the situations that we've seen more recently in the news with regard to AI and ethics are those situations where people, again, they have that autonomy bias. They are thinking that the system might be able to manage what was mentioned earlier was a resume system, thinking that if we use an AI system to look at these previous resumes and then to be able to identify new applicants who would be really good matches within this organization, by using that AI system somehow will reduce the amount of bias that we've seen in our hiring in the past, and perhaps we'll be able to get a more diverse staff. Unfortunately, as was mentioned earlier today, what we see is if you start with biased information, so if the resumes are all of existing employees and those existing employees are not diverse, what you're going to get is, unfortunately, a result of not a diverse group of applicants, because the people who don't fit into that standard, the people who are outsiders, if you will, from the point of view of those resumes, they aren't going to be selected by an AI system any more than the people were selecting before. So you really have to change the organization. You have to change the way work is being done. You have to have a different set of data. And often that lack of good data is one of the reasons why an AI system may not be right for a particular problem. So the humans have to be accountable, but also we have to think ahead as far as, is AI the right solution? Is this really the best way to solve this problem? And that's another way we can be accountable for the systems we're building.
Great, Carol, thank you. I do see one more question here, so maybe we can address that really quickly and then wrap up. Could you share any thoughts on AI ethics that are used by the DoD for defense?
Yeah, certainly. So as was mentioned earlier today, the Defense Innovation Board and the Department of Defense have approved and are using a set of AI ethics principles, and that is being used right now in the work that's being done within AI. So they include things like, making sure that the system is governable, making sure that decisions are being left to a human when life is at stake. And it's really important, and I'm actually very excited about the fact that they're using these, because it is, while it does end up making things take a little bit more time. This is work that we need to stop and think about. We really need to make sure we're doing the right things, that these systems are working the way we intend, and that we are making sure that we're doing the right thing with these systems so that we can work smarter and ideally not as hard, but definitely smarter. Great. So thank you for joining our Q&A, and I wish you all luck making smart and ethical and really trustable AI systems. This is really important work, and I look forward to future conversations. Thank you.
Hello, my name is Eric Heim. I'm the principal investigator on this project called Knowing When You Don't Know, Engineering AI Systems in an Uncertain World. And the big idea here is that in order for the DoD to use AI, specifically machine learning, there has to be this idea of calibrated estimates of uncertainty with the predictions that machine learning models give us. Not only do we have to be able to quantify this uncertainty, but able to reason about it and potentially rectify it in our models. So I'm going to use this illustrative example sort of like to illustrate what I mean by uncertainty in machine learning predictions and why they're important. So imagine you are an intelligence analyst that is trying to find a particular car from overhead imagery. This is something that machine learning is actually pretty well suited to do. So modern object detectors can conceivably do this task. And potentially what could happen is if the machine learning model or this object detector will say, hey, I think that there's potentially two places where this car could be, either this one on the left highlighted by the right or the red box here, and as well as maybe potentially on the right here and highlighted in the red box. But also typically what comes equipped with these predictions in these models is this quantitative estimate of their confidence or conversely their uncertainty in their predictions. So in this particular example I'm showing, this is suggesting that the model is suggesting that the prediction on the left it's 97% confident, while the one on the right it's 98% confident. And if you're an intelligence analyst and you look at these two predictions with these confidence measures, you may say to yourself, well, both of these predictions are very confident, but the car can only be in one place. What do I do? And this isn't just sort of examples that I cooked up here. This is actually well known within the machine learning community that modern neural networks, such as the ones that could be doing that task we just talked about, are drastically overconfident in their predictions. And what this means is that they'll almost always predict with high confidence, regardless of how likely they are to be correct. What would be more useful is a calibrated estimate of their confidence, or conversely their uncertainty. And so this is ones that roughly indicate how likely the model is to be successful in their inferences. So instead of the confidence predictions we had before, if we had the ones here, what you'll see is, potentially the one on the left is actually considerably less confident than the prediction on the right, or the inference here. And what this allows a human to do is say like this, an analyst in this case, allow humans to compare these inferences and then make assessments about which ones that they should eventually take action on. So if the intelligence analyst wanted to say, I'm going to dedicate resources to one of these two things to find this car, the one on the right is probably more likely, and the analyst can do so with more confidence. And this brings us to the mission statement of this project. So in order for the DoD to leverage recent advances in AI, modern machine learning techniques must be able to quantify, reason about, and rectify the uncertainty in their predictions. In this work, we'll benchmark modern techniques that will quantify uncertainty, but we'll also develop techniques to identify causes of uncertainty and efficiently update ML models to reduce their uncertainty in future predictions. So like I said, there's sort of the three. There's the quantify, rectify, and reason about. I'll go over each one of these very, very briefly. So first of all, quantify. What I mean by this is how do we have techniques for quantifying uncertainty in predictions practically perform compared to each other? And if you look at sort of the literature as in this field for in machine learning, you can sort of bin a bunch of the techniques. So for instance, we've listed a couple here, papers that are from the post-training calibration literature, as well as Bayesian neural networks and deep ensembles. What's not well understood is how these methods practically compare to each other. So not just in how well they can calibrate confidences, or how can they quantify uncertainty, but also, what is their constraints on data? How much data do they need to actually get this level of performance? Or, how much added computational expense is incurred by using them? So one of the first tasks we'll be doing in this work is be able to actually benchmark these modern techniques so we can understand the practical trade-offs between using them, so we can then potentially apply them to some of the DoDs and problems with this knowledge of their practical limitations. The second one is detecting cause of uncertainty. So what we're asking here is, how do we detect why a deployed model became uncertainty in its prediction? So imagine if you deployed that object detector and then suddenly every prediction it gave was uncertain. Certainly identifying the cause of that uncertainty, then allowing us to iterate on that model to improve it, it's very important. So first we need to detect that there's the cause of this. And so we're looking at two of the potentially many causes of uncertainty that can cause this performance degradation or this increased uncertainty over time. One of them is dataset shift. Basically what this is that the distribution of data changes from what the model was originally trained on. So you can imagine something along the lines of, well, we trained this model, or the model learned its parameters when it entirely on pictures of the aerial images of the summer. And now suddenly, as the seasons change, there's snow on the ground. And so there's something fundamentally different about those two distributions. And so suddenly our model may be very uncertain in all its predictions because the imagery that's being fed is very different. So there's some work that we have with one of our collaborators, Zach Lipton, we want to extend and be able to explicitly detect when this data set shift happens. And we want to extend it to the case where we're able to find the direct cause of this uncertainty. And the other potential cause of this uncertainty could be the emergence of novel classes. So maybe suddenly you have a new model of car you want to detect, but you don't have any training data for that. But so how do you be able to reason about these novel classes as they emerge? So one of the lines of work we want to do is be able to detect, using something called open world models, the emergence of these new classes as they arise in the deployment environment. And finally, we're going to talk about rectifying these models. So once you're able to quantify and detect the cause of uncertainty in a model, and we identify this as a persistent issue that in the deployment environment, how do we rectify this? So once the uncertainty is detected and quantified, how do we make models more confident in uncertain cases in the future? Now, one option is to just simply take all the offending or the really low confidence cases into the deployment environment and have a human sit there and label them correctly. So if we now have these snowy scenes, we have a bunch of labels associated with them that are given by domain experts, and then we retrain our model. Now, the challenge with that is that labeling all of these instances can be very, very human intensive. So maybe we don't have the resources, or we want to reduce the cost, the human cost, in having people label all of these instances. Or so, for instance, in the object detection case, these analysts' time it's valuable because they're trying to perform their mission needs. So one of the approaches we're going to investigate for that is active learning, basically choosing the most informative instances to have humans label instead of just all of them. And then the other potential challenge is retraining, validating, and deploying a model can be very time intensive. So if we had to go all the way back, into the model development stage, and then really do this heavyweight audit of the model and have experts toil over the different potential reasons why this could happen, and then go through the process of maturing that model and then deploying it in the environment, can be very time intensive. And so what we want to be able to do is to be able to develop best practice to make that process as quick as possible. And when appropriate, we want to do something called online learning, and that once we get new instances to learn from, just update our model in situ. Now, the situations for that are often very rare because updating a model in situ has its own risks, but we may be able to identify cases where we can safely do that. So I just want to give one more perspective on uncertainty AI systems, and this is from the AI engineering perspective. And you've heard a lot today, obviously, if you've been following some of the other talks about what AI engineering and the SEI and our efforts there. But I want to show sort of what this means in terms of this project. And so when you look at the academic literature, they sort of view machine learning as this pipeline you see before you, where you basically have some data, you pre-process it, your ML model makes some prediction, directly to a human, but really in reality, it's a much more complex process. So you may have multiple different modalities, and there may be multiple other different system components that do multiple different things. Now, the good thing about having calibrated estimates of uncertainty is that it can actually inform these other components downstream in the AI system. So if the model, for instance, is very uncertain in all its predictions, the system as a whole can determine that those inferences from the model are now unreliable and have mitigation strategies in place. So this actually implies that uncertainty quantification or calibrated estimates of uncertainty can actually increase the robustness of your ML system or your AI system. And similarly, if we by having these detection and rectifying best practices, this allows us to iterate better on these ML components instead of having to go engineering these AI systems by these heroic efforts that potentially have to happen if you don't have these best practices in place. So I just want to really just wrap up here with, again, the restatement of the mission statement. We have some awesome people within the SEI with a variety of backgrounds that are working for us. So that we have Jay, who's an awesome AI engineer, Carol, who's a user experience expert, and John, who's also a fellow ML researcher. But we also have 2 campus collaborators, both from the machine learning department, but Zach has a appointment in Tepper Business as well. So Zach Lipton and RT Singh, and they have they have a long history in studying these types of problems, and we're really excited to work with them. And finally, I just sort of wanted to put this slide up here for everybody to see. So what all the people out there viewing this video, how do you work with us? And so this project is just starting. We're legitimately looking for these really killer apps in the DoD. We have some lined up, but we really are interested in hearing the problems they have. And so if you have some domain expertise in a domain for which ML can be applied, that's something we're absolutely interested in. If you have mission relevant data that we can use, that's great. Even if you just have a problem that you know that ML, you feel though that machine learning or AI can solve, we're interested in that as well. So we'd love to talk to you. So you can send an email to this info link right there. And thank you for your time.
Ooh,
I'm John Wolbier. The title of my talk is Topics in Advanced Computing, Promise and Challenges of Recommendation Systems in the Department of Defense. This is work I've done with my colleague Scott McMillan at SEI, as well as results of collaboration between Professor Zmeng and his student Elliot Binder at CMU Electrical and Computer Engineering. I'm going to give you an overview of recommendation systems, talk about concepts and foundations, talk about applications to the Department of Defense and the intelligence community. Then we're going to spend some time talking about a very popular recommendation system right now, DLRM, Deep Learning Recommendation Model. It's popular because of its presence in the MLPerf benchmark suite. We're going to talk about aspects of advanced computing within DLRM and in the ETC, and then some of the results from the collaboration with CMU SEI. So what is a recommendation system? Well, given your profile and the things that you've liked in the past, what's the probability that you're going to click on a recommendation? So if you've used Netflix, Amazon, YouTube, Spotify, Facebook, or Twitter, you have interacted with a recommendation system. It's what gives you your next movie to watch, or your next product to buy, or your next video to watch. Facebook has said that DNN, deep neural network-based personalized recommendation models, are up to 80% of their AI inference cycles in a production scale data center. This is a huge number of cycles, and it points to the importance of recommendation systems. So the idea behind recommendation systems, again, is given a user an item that the user has not interacted with, what's the probability that a user will click through on an item? So a good way to think about this is by this matrix. And so we'll use the Netflix prize data set sort of as our motivating example. Think of the rows as representing different users, and then the columns representing different movies. Not every user has watched every movie, and the movies that the user has used, they may have entered a rating in the individual spots, in the individual pairings. The idea of the recommendation system is to fill out this matrix. So predict a rating for all movies for each individual user. One thing that's important about recommendation models is the sparsity of the data. That is, any given user has interacted with very few items. And so again, using the Netflix prize data set, we can think about this sparsity. So imagine we have about 20,000 movies and we have about 500,000 users. That's 10 billion combinations. So if you wanted your user by movie matrix, it would have 10 billion elements almost. On the other hand, the ratings of 1 to 5 have only been given for about 100 million of these pairings. So what does that mean in terms of sparsity? 100 million over 10 billion is about 1%. This matrix actually has 100 entries. So if we wanted to represent a sparsity of 1%, that would just be one of these empty spots filled in. But for visual clarity, we filled a few more in. But the main idea is still that you want to predict what values to put in the empty spots. So recommendation systems in the Department of Defense and intelligence community come in many different flavors. So within the field of intelligence analysis, you can imagine that the number of documents that are available to analysts is much, much greater than the number of analysts. And so how would they prioritize what documents to read? And that could be provided from a recommendation system. Similarly, a novice analyst could be guided in their search using paths from more experienced analysts. In the field of cybersecurity, there's a long list of applications generating prioritized lists for defense actions, detecting insider threats, or an important one is as an attack vector. And what I mean by that is, since there is all this commercial use of these recommendation systems, adversaries can attack those recommendation systems to turn outcomes toward their desired outcomes. In which case, cybersecurity analysis has to be analysts have to be aware of recommendation systems. Similarly, in social network analysis. We have discovery of fake news or identifying malicious conversations and groups. More specifically, the JAIC is the Joint AI Center. That's the Pentagon's point of focus for the AI mission. The JAIC has 6 different mission initiatives, all listed here, and recommendation systems are appearing within these mission initiatives. The first example is Kitware, developing and demonstrating the interactive query refinement with intelligence imagery, and they're actively developing this capability and migrating it to Project Maven. Within the Joint Logistics Mission Initiative, there's been work on operationalizing AI for predictive maintenance within helicopter engines. In this case, it's an active learning scenario where you train an AI that provides results to users who can quickly approve or reject results, and then at the same time be doing unsupervised data exploration to generate candidate questions that a user may want to ask the AI, and then use this model to recommend future questions to the user. If you're interested in these applications, you can contact Dr. Juan Vasquez at AFRL. MLPerf is a collection of benchmarks. It's a community-wide effort. It has become very popular in recent years. It's a community-wide effort to develop benchmarks for evaluating vendor hardware that represent real-world problems. It includes many, over 70 in fact, companies that are involved with AI ML hardware. It also involves universities and research institutes, with including all the big names in research institutions. MLPerf has DoD relevant benchmarks within it, and namely the image classification and object detection benchmarks are very relevant for DoD, as is the natural language processing elements and benchmarks. Recommendation systems have also been part of this activity, and most recently, Facebook's deep learning recommendation model was recently added to the MLPerf benchmarks. Because of this, it is receiving a lot of attention from, like I said, companies and universities and research institutes. And it's providing an excellent way for people to study the details of these models and learn about their performance and their performance characteristics. I want to talk a little bit about, again, expand on this idea of the matrix of users and movies, and how a user-movie pairing is one prediction, and how a model might represent that. So again, the size of this matrix could be 10 billion or more, larger. And you don't actually want to store that 10 billion sized matrix. So how do you get a prediction for an individual user and an individual movie? This is a technique called matrix factorization that's used. The idea here is you represent users by a smaller number of entries. So the total number of users is going to be the same as this dimension, the total number of users in the expanded matrix. Similarly, the total number of movies in columns is going to be the same as the total number of movie columns in the expanded matrix, but the inner dimension is much shorter. Only a handful of values represent any particular movie, or and that same smaller number of values represent a particular user. You think of these as being floating point values or integer values that somehow represent the user and somehow represent the movie. And then when you want to make a prediction or a pairing, you multiply this vector by this vector, and it gives you a value that appears in the matrix. These are what are called latent factor vectors. Latent factor vectors. In that latent means hidden, and we don't exactly know what the numbers that appear in these vectors mean. They are trained against the data, but we can't assign an exact meaning to them. On the other hand, it's useful to think about these things as features. So for example, one might think of the features of the user being gender, hobbies, income, country, age, or party, and then the features of the movies being genre, soundtrack, director, producer, actor, year. Again, this is sort of notional because really once you train on the data and you arrive at these numbers, you've sort of lost the meaning, but it's a very useful construct to think about what these vectors mean. This is DLRM, Deep Learning Recommendation Model, released by Facebook in 2019. This is a recommendation model that does a click-through rate prediction. Users and products are represented by continuous and categorical features. So the user is represented by some number of features here. Those features are fed into a neural network or a MLP, multi-layer perceptron. Also, the categorical features, like that actually describe sort of the item or the website or whatever it is, those are fed into embedding tables. This data is interacted with each other, concatenated, and run through another neural network, resulting in a click probability. One of the important parts, and we're going to talk about this now, are these embedding tables and this categorical features. In the data set used with MLPerf, there are 26 categorical features. Each one of these categorical features is represented by a table that has a variable number of rows. You can kind of think of it as this picture. Some of these tables might be small. There might be 3 rows and 128 element vectors. Some of the tables might be very large, 40 million, for example, representing a category within the categorical feature. And the reason I'm spending time on these is because they play a major role in the performance of the model on hardware. So there are many aspects of advanced computing that are present even within DLRM. And some of those, a small selection of those, are shown here. Similarly, I have a list of some past and present projects within the Emerging Technology Center. And this matrix, I've filled out some entries showing which of our projects have approached which of these different topics within advanced computing. So parallelism is a major topic in advanced computing. Data level parallelism, model level parallelism, the type of model level parallelism, hardware level parallelism. SIMD is single instruction, multiple data. SIMT is single instruction, multiple thread. Different specialized kinds of cores for doing to accelerate compute. In fact, specialized application-specific integrated circuits are being designed presently and sold specifically for these kinds of workloads. And you can see that within the ETC, we have experience in all these different aspects of advanced computing. The one I'm going to focus on today is this last one, data motion. Data motion really underpins all advanced computing and all of computing. So we'll look at data motion and how it manifests and how it plays a role within DLRM. So first of all, what is data motion? Well, data motion is the most expensive part of any calculation. That's the first thing to remember. Expense could be measured in terms of time and energy. It's both. So it's the most expensive thing your program does. What it refers to is moving values between memory spaces. So I have some cartoons here sort of showing a conveyor belt that's conveying data to a place where it can be worked on. So you can imagine you have a person standing here, and when they get their value of A and B, they do the addition, and then they hand the result C to someone else. There are 2 types of memory boundedness that this can represent. The first one is bandwidth boundedness. That means that the data pipe is full. So you can imagine this conveyor belt clicking one step forward every second, and the data is completely full, and every second the person here gets their value of A and B, and they add it together, and they hand it off, and they can't do it any faster. They can't produce results any faster because of the data pipe is full and it's being delivered to the processor at the maximum rate possible. This kind of characteristic, this bandwidth boundedness, is something you find in dense structured workloads. In the field of AI ML, you want to think about sort of computer vision. Images and pixels have structure in how the data is laid out in memory. The other type of memory boundedness is latency boundedness. That is where the data pipe is not full, and you spend your time waiting for the next pair items of data to be delivered to you so that you can do your work. This kind of performance characteristic appears in workloads with random access to data. So a good example of a random access to data would be a graph data structure, where you're interested in, you have a node in a graph, you're interested in neighbors and neighbors of neighbors and neighbors of neighbors of neighbors, but you can't get those neighbors of neighbors of neighbors until you have the neighbors of neighbors. And only then do you know the address in the memory system where you can request the data to do your calculation. Math is fast, data motion is slow. What I mean by this is in modern computing, you can do multiple mathematical operations in any given clock cycle, whereas it takes multiple clock cycles to do any one data operation. So think access to main memory is hundreds of clock cycles, where I can, if I had the data, I could process multiple of them at one time. So now back to DLRM, now that we know what data motion is. So we're going to focus on this part of DLRM and figure out where the time is spent within the calculation. These embedding tables shown here are on the side here. This center part here refers to the pairwise interaction, and then the concatenation is this part here. So we have a dense feature vector coming from the bottom neural network, the bottom MLP. But then we also have all these tables. And again, in the DLRM case, there are 26 of these tables. And for each 26, we need to pick out one row from that table based on the input data. So these tables, again, they can be of size 3, in which case there's only one of 3 you would pick for each categorical feature. But they can also be sized 40 million. So you only need to pick out one row in 40 million rows. DRAM access is slow, and this is where time is going to be spent. However, once you get all those rows, you put them together, and you do what's called the interaction, where you sort of do a mixing. You're multiplying each row by each other row to give you a measure of the interaction of the different categories or the different categorical features. And then you append that data again with the dense feature that came from the bottom MLP. So to look at where is time spent in this whole thing within DLRM. The dense feature, this would be the MLP I'm referring to, is what we would call fast. That's this fast vector math. At the very worst, it's bandwidth bound. If you go back to what I talked about on the previous slide, the bandwidth is the pipe to the processing unit is completely full. On the other hand, all these random accesses to main memory is very slow. Again, hundreds of times slower than this math is the DRAM access. The actual math doing the interaction is also fast. The process of concatenation is, again, a data motion process where you have to move data from one location to another location, and then you have to move data from this location to this location before you can send it on to another fast top MLP, multi-layer perceptron. So now I'll talk a little bit about the work we've done on this with with Professor Zemeng Lo and his student Elliot Binder at CMU ECE. So Professor Lo's group develops hardware performance models to write optimal code for various platforms. These models then get incorporated into the Spiral framework, which is something from Professor Franchetti at CMU ECE, ultimately to automatically generate optimal code. AI models are overwhelmingly implemented in Python frameworks such as PyTorch and TensorFlow. These Python front ends then are linked to high-performance hardware-specific backends. However, the high-level abstractions in these models introduce performance trade-offs that you can get around if you are willing to write hand-tuned specialized code. Well, it's important to write hand-tuned specialized code that's driven by performance models so that you know what you're missing. So what Professor Lo and Elliot Binder have done is to do an implementation both for CPU and GPU that exploit their expert knowledge of the memory systems in the hardware to minimize data motion, and specifically make use of their understanding of the set associativity of the cache to maximize the delivery of data to the compute units. So the results that we're going to show in a second are applied to both CPU and GPU implementations. They have performance models for both of these kinds of hardware. These results are new results that will be presented at conferences in coming months, and will be held up as the best possible performance that the community can be expected to achieve in their workload. So what we have here is several results. So going across the bottom, the first 4 columns are CPU results. The second 4 columns are GPU results. The first 2 refer to the small sized model within DLRM. The next 2 refer to the MLPerf, or the DLRM MLPerf sized model, and similarly small and MLPerf for the GPU. What is on the left is the performance profile for an out-of-the-box PyTorch implementation. And then the corresponding implementation written and executed by Professor Lo and his student. The green refers to batch matrix multiply, because ultimately that, once you have the data motion done, it's really just a batch matrix multiply. Well, it turns out that they can get, in this case, up to 5 times performance improvement against an out of the box PyTorch implementation. 5 times. It's over 2 times in the larger data set size. The size of the data set has various implementations and forces you, or suggests different choices to make within the implementation. Similarly, for GPU, we're over twice as fast as compared to the PyTorch reference implementation. So what do these numbers mean? Well, this is if you want to look at it in terms of financial savings, this is a very back of the envelope sort of rough estimation of what we're talking about here. So in the commercial market, the hyperscale data center market in 2025 is projected to be $100 billion. So if, with a conservative estimate, 10% of data center time was spent on recommender systems, that 10% would correspond to $10 billion. If you had a model that went twice as fast as its competitor, you're talking about $5 billion worth of hardware that you might not need to invest in. Again, this is not saying that we saved $5 billion. This is sort of illustrating the magnitude of the issue here. DoD's budget is, while very large, is significantly smaller than the total commercial market. So the FY21 AI budget proposal for DoD is approaching $1 billion. the DoD will definitely spend hundreds of millions of dollars on inference and training in the coming years. And applying these kinds of savings where you can double the performance of your models will translate into tens of millions of dollars in savings. Again, this is the idea here is to give a sense of the magnitude of the problem. Lastly, I want to close with introducing our advanced computing team in the Emerging Technology Center. Myself, Scott McMillan, and Annika Horgan, we work on the DARPA projects that we're involved with. Software-defined hardware is one. Scott and I also work on the Spiral AI ML project, which I touched on in terms of how Professor Lowe's performance models feed into the Spiral project. We have activities in quantum computing primarily from Jason and Dan Justice, and most recently we've started a project called the Quantum Advantage Evaluation Framework. And then last but not least, Professor Zemeng Lo and Elliot Binder, we work with them closely to get their information and get it out to DoD and IC. With that, I'll take any questions. Thank you. Thanks for joining us today. I'm joined here by my colleague, Scott McMillan, Dr. Scott McMillan, who's off screen. He and I are going to see if we can answer any questions about the talk we just gave. Scott, is there anything that people want to know about?
Sure. I have a question here that asks, can you talk a little more about the different types of parallelism in deep learning systems? And then have you ever considered mixing the different types of parallelism?
Sure, I could talk about that. So the first thing about parallelism in deep learning systems, the first differentiation will be internode versus intranode. And so intranode, and really the thing that defines these two types of parallelism is the memory space. So in intranode parallelism, all data is in the same memory space, and all parallel resources have access to the same data. This you want to think of like OpenMP threads kind of stuff, or single instruction, multiple data, those kinds of things. Internode parallelism is going to be where the model is resident across multiple memory spaces. So in this case, you want to think of, a compute node has a memory space, and the parallelism is going to work on for a particular compute node. There's going to be all the work's going to be done on that compute node, but then other compute nodes, which are in different memory spaces, have to communicate, with each other. So with that sort of setting, we'll talk more, focus more on internode parallelism. So if you think about deep learning parallelism in an internode situation, you really have a couple different kinds of parallelism. So the first would be what's called data parallelism. And this is where you take your deep learning data, which can be very, very large, and you spread it across the compute nodes, for example, across lots of compute nodes, and you have lots of compute nodes so that you have a lot of memory space so that the data can reside on these different resources. So what's sort of not obvious maybe immediately about that situation is that the model itself, the deep learning model, is going to be replicated across these compute resources. So you'll have an instance of your entire model on each of your compute resources. Each instance of the model is going to see different data. And so if you're doing something like training, what happens is each individual compute node will come up with different updates to the model, and then those updates will have to be communicated across all the resources, and some sort of aggregation step has to happen. So the other kind of, or another kind of parallelism you can have is model level parallelism. That is, you take your model and you split the parts of it up across these different compute resources. So you can think of doing this a couple different ways. One is you can do interlayer parallelism, where you put different layers of the neural network on different resources, or you can do intra-layer parallelism, where you take any given layer can be spread across these compute resources. And these parallelism models get kind of complicated kind of quickly, and they each have sort of their own issues that are associated with it. As to whether you can mix the types, DLRM, the way we talked about it, as it appears in MLPerf, is a sufficiently large model that it kind of naturally does mix the modes. And what I mean by that is, at a high level, it's data parallel in terms of your input queries being spread across the compute resources. However, the nature of these tables, they're very large tables. If you remember, in some cases, you've got 40 million entries of 128-bit vectors. One of these tables itself can consume, in the tens of gigabytes. And you have, again, 26 of these tables in the MLPerf instance of DLRM. Not all of them are 40 million, but some of them are. And so basically all 26 tables will not fit in the memory space, if you're thinking about GPUs, for example. All the data won't fit in one GPU's memory space. So the sort of the input data has to be spread across these resources. It has to be done in such a way that any compute node can get to that data. And there, in fact, in the implementation of DLRM, there's a sort of an all-to-all communication pattern that has to happen so that all compute nodes can get access to all the data, even though it's over some sort of communication network. So you can tell, I've talked about it for a little while. It's not a trivial matter, and it's a sort of an aspect of advanced computing, and one of the things that we think about.
Excellent. So we have some audience questions here. First of all, Robin asks, are the model algorithms and low-level rewrites published or proprietary?
So the results that I showed today have been submitted to the IPDPS conference. That's the first author on that work is Elliot Binder. And then Zemang and Scott and myself are on that paper. Scott, when does that conference happen?
That happens in May of every year.
Okay, so I mean, we could maybe, I guess we'll probably have to wait for acceptance to see if it's accepted, but
yep, that usually happens in January.
So yeah, so it will be soon to be published, and it's the results and it's the details about how those results were achieved.
Right, and then we have a question from Katie, and she's asking, can you go into what the quantum framework is?
So sure. So we have some work in the quantum field. I think there might be a poster in the next session. Is it from Jason Larkin?
Yes. That's right.
Okay. So Jason will go. I mean, the first answer to the question is go look at Jason's poster, and you'll hear all about it. A summary sort of is we're in what they call the NISQ era, the noisy intermediate scale quantum era, and there's a question about whether in the next 5 to 10 years there will be a quantum advantage for DoD relevant applications. And so Jason and his collaborators are working on evaluating the status of classically implemented algorithms and comparing them to their quantum peers, and working with various stakeholders and collaborators to make sense of this space. Many of these algorithms are in sort of combinatorial optimization and those kinds of things.
Now we have a question about the spiral framework. What high-level language does a user write to in that framework?
Actually, Scott, I think you're probably better suited to answer that than I am.
And it's a mixture. It can actually recognize a number of different DSLs. Right now, it uses something called Sigma SPL for its digital signal processing algorithms. It's a high-level math language, but we're also integrating a what's called the GraphLaws template library, so it understands the interface for graph algorithms as well. And then we have another question from the audience. Nick is asking, many times on-paper savings get turned into capacity for improved performance. Is there a backlog of capabilities that could fill the void?
I'm not sure I understand exactly what the question is. I mean, so is the question like if you save time, then what are you going to do with that time that you've saved? And in that sense, there's always more work to do. Is that your understanding of the question, Scott?
That's my understanding. And you know, honestly, my initial response to that question is that we could use that savings to increase the size of the model or increase the throughput. So it depends on what the application needs. Does it need a larger model to improve accuracy, or does it need to get to answers faster? And you could probably use those kinds of savings either way.
Yep.
So that's all the questions I have from the audience right now. Do you have any final thoughts?
Well, if you are interested in what you saw us talk about, this is a topic we're really interested in. We're engaging with the MLPerf community as a whole. Again, we're particularly interested in applications of deep learning and AI to sort of DoD relevant problems. But if you have anything at all you want to talk about in this space, I think you can feel free to reach out to us. I imagine they're providing some sort of contact links. And I think with that, we'll wish you farewell. Thanks so much for joining.
Thanks for listening.
Welcome back to the SEI 2020 Research Review. I hope you've really been enjoying the sessions all day. I'm sort of here in the next few minutes to wrap up a little bit on some of the stuff we've heard on the theme today, which is all a bit around AI engineering, and then to encourage those of you that are registered for this to move from here into the poster sessions. Now, in the poster session room, sadly, I don't have wine and cheese and beverages and other kinds of things to offer you on this particular occasion. But what I do have to offer you is a direct one-on-one interaction with the PIs that you've been hearing from and listen to the posters as they present that. So basically what I'd like to do is to sort of run through a little bit what you've heard today, and then let's get right into the poster session so that you can start to interact with the different PIs. So, we started the day with the introductions from our CEO, Paul Nielsen, from our Vice President of Research, Michael McQuaid, and they really opened it up, I think, very well, especially when Michael really talked about, we've got these fundamental questions surrounding AI, and those fundamental questions sort of on the, how will we know? What will we learn from AI? When will I know it? How will I know how it gets attacked and defended? And these fundamental questions showed up again and again in the different sessions that we talked about through today that went into it. Matt Gaston, when Matt came into it, I thought maybe one of the phrases that he caught, which was attributed to Michael McQuaid, but really caught the day, was, we're here to help DoD really do the best AI as well as it can be done. And that kind of spirit in terms of coming through and deciding what the AI system is going to be like, that's really what the sessions today were kind of all about in a nutshell. But we went through a lot of different aspects of this, from data cleaning into the elements within the panel talking about CI/CD for AI/ML, the importance of education, the importance of trust, and coming into this, all of the different aspects of what does it mean to attack an AI system, to really defend against those attacks. And then I thought a really nice transition from the attacker was really kind of get into the ethics and the ethical structure. It isn't enough just to defend AI. You have to actually make AI ethically sound, and sound in terms of exactly how are we going to be working these particular systems. So those were the kinds of elements that I thought really went together. And then, of course, as we got more into later on in the afternoon and started talking in detail about how it is that some of the hardware and software come together to do the co-evolution of AI within hardware and software, and how are we going to bring that all together in the future of AI engineering. Those are the kind of areas that you could see from the presentation really get into building on everything we understand, from the details of matrix math to the details of programming languages and understanding programming structures, to the entire element of what does it mean to drift, what does it mean to use some of the data and things that are there. So again, really does point out some of the special aspects of what's been happening through all of this. So our key insights that we came into through the day have really more to do with those areas around AI engineering. Now, we're going to be transitioning tomorrow into other sorts of things that the SEI does in cybersecurity and cyber engineering. So really, I think tomorrow is going to be another very, very exciting day when it comes into it. But when you look at these 4 days as a whole, one of the things I'd really like you to keep in mind is that these 4 days get to the heart of what the SEI does, which is its 4 unique capabilities that it's been doing ever since 1984. Create software that's affordable, that's timely, that's capable, and that's trustworthy. And that's whether I'm talking about traditional software engineering, cybersecurity, AI engineering, any of these kinds of areas that we're moving forward. And that's really where we're trying to strive from. But I think the other thing you get from today, maybe even more importantly, is just the people, right? I mean, what is it that really makes these? It's really the people that, foundationally make what it is that's special about being at the SEI and sort of doing the work. So I think if you really have seen something that resonated, it really is because of the individuals that you saw presenting today and their entire team behind them in terms of what was working on that way. So that is the nature of what we're doing here. It's the nature of the kind of work that we're doing. I really hope that you will continue to join us tomorrow as we go into the rest of this. But for now, more importantly, those of you that registered, you have your links. And you're going to be able to go straight from here into the poster sessions and really begin to do that close interaction one-on-one with the PIs. Ask your questions. Get the answers that you really need to have. By the way, today, I will say that I love the questions that were coming in. I mean, especially from some of these people like Patty, wonderful questions that sort of came in that we got to answer. And it's because of your questions and your interest that we really wanted to put this program together and really sort of make it go. So I thank you again for joining us today. I thank you for listening to the presentations and interacting with us. I look forward to seeing you again tomorrow, and we will go from there. And on that, thanks very much.